Okay, we're on. Once again, welcome to the Speaking Logic background course of the 10th Summer School on Formal Techniques. My name is Shankar, I'm from SRI, and I will be lecturing for the first two sessions, and then Stephane Graham-Lengrand will take over from me for the third session on type theory. So today I'll be weaving in and out of VS Code PVS to illustrate some examples. And we'll be talking about the proof rules of propositional logic, equational logic, first order logic, and higher order logic, and seeing how we use them. And then we'll go into two somewhat of advanced topics, namely our logic and model checking. First, a quick review of what we covered yesterday. So we talked about abstraction engineering as a significant activity that we engage in, and the role that logic plays in supporting abstraction engineering. Abstraction is really the only way to kind of gain mastery over complexity, over scale. And this is why logic has been unusually effective and unreasonably effective, ironically enough. In this course, we're really learning to use logic as a modeling framework with facility and seeing how we can build formal proofs using concrete representations of abstractions as logical formulae. So we looked at some problems and the paradoxes and saw the need to actually secure the foundations of any subject for that matter. We looked at some interesting theorems like the Nancy theorem and Cantor's theorem, and looked at some proof exercises that you should undertake. And we examined the role of visual proof and why symbolic representations don't really sacrifice anything in terms of the visual perspicuity. Okay, we looked at some naive set theory operations. These are all basic concepts that you need in building logic. Finally, we looked at the lambda calculus notation, where we saw the use of lambda as a binding operator, so that lambda x dot followed by an expression binds the free occurrences of x in the body of the lambda expression, so that when you apply the lambda as a function, say lambda x squared as a function, say you apply it to 3, then 3 gets substituted for all the occurrences of the free occurrences of x in x squared. And these are codified by a set of rules: alpha conversion, beta conversion, eta conversion. So note that so that's those are the rules. Finally, we looked at the semantics of lambda calculus modeled in hereditary finite set theory, so that you can actually think of lambda expressions as represented by sets that are then encoded as numbers, and you apply it by essentially looking at the finite subsets of a set. So that's the notion of application and so on. Then we looked at Turing machines as a form of computability. We looked at some theorems about computability. We didn't go over them in any detail. And finally, we looked at this notion of logic as the trinity between language, meaning, and proof. So that language restricts the what you can write, meaning indicates what these symbols actually are to be interpreted as. We also realize that some symbols have fixed meanings. So the lambda in lambda calculus is fixed. You can't then use lambda as a variable, or you can't use dot as a variable, and so on. So the idea is that some things have fixed meaning, because if you don't fix the meaning of something, you can't say anything. But on the other hand, you want some symbols to actually be variables, because you want to make statements that apply to more than one thing. You want statements that apply to anything, for instance. And so, certain things are allowed to vary. And in particular, when we looked at propositional logic, the meaning of and, or, not, etc., are fixed. But the meanings of P's and Q's are allowed to change. And so therefore you can substitute, it is raining, I need to take my umbrella, uh, I need to work in the garden. All these are conditions that you can then bind to the propositional variables and derive things that are true of the world out of them. So in first order logic, you'll see that you have function symbols and predicate symbols, and those two in some cases are allowed to vary, and in other cases you want them to be fixed. So for instance, if you're doing arithmetic, you want the meaning of plus and times to be fixed, but you may allow other symbols to, like p's and q's, to vary. And so this is a fairly important point. And finally, the notion of proof is important because it gives you a kind of constructive way to establish validities, an effective way to establish validities. So we looked at propositional logic as combining propositional variables into formulas by means of negation, disjunction, and conjunction. We looked at the truth table interpretation of these connectives. This is what I mean by the meaning of or is fixed. This truth table fixes the meaning of or. This truth table fixes the meaning of and. Then we looked at how you can compositionally compute the meaning of larger and larger formulas, starting with the assignments to the variables. Then we looked at how you can define new connectors from these, and these are some exercises that you can do. Most importantly, we looked at the notions of satisfiability and validity. And you can think of these as judgments about formulas. Now, if I just write down a formula, say, A implies B, it's just a formula. It doesn't really, carry any sense that I intend it to be true or false, for instance. So you have to make a judgment about it. You can say this formula is valid, this formula is satisfiable, this formula is unsatisfiable, or this formula is provable. So those are judgments you make about formulas. And in particular, you can say, for instance, that if a formula has a model, it's satisfiable. If it has no model, it's unsatisfiable. And if the negation of a formula is unsatisfiable, then the formula itself is valid. And there's a notion of entailment that every model of phi is a model of psi. And you can actually test for it by checking whether phi and not psi is unsatisfiable. Because this would mean that if it was satisfiable, then there is a model of phi that is not a model of psi. And hence, you've got a counter model to the claim of entailment. Okay, then we saw that propositional logic is actually quite expressive. And now we start looking at proof systems for propositional logic. Any questions at this point? Okay, I'll continue in that case. So we'll look at three different proof systems. So the first is the Hilbert proof system, where your judgment is of the simple form, A is provable. And we can have Hilbert proof systems with more connectors in them, but we'll choose one that just has implication as the only logical connector. And in this proof system, you can start by the judgment that A implies A is provable. So that's what this is saying. It's an axiom. I don't need to depend on any further premises. There's nothing above this line for me to depend on. So A implies A is provable. Then you can say that A implies B implies A is also provable as an axiom. And you can say, for instance, that if A implies B implies C, then A implies B implies A implies C. So roughly speaking, this part of it says that you can prove C. C follows from A and B, roughly speaking. So if you have A and you have B, then C follows. And in particular, if B already follows from A, then you do indeed. If ever you have A, then you have both A and B, and hence you have A implies C. So that's what this is. And then finally, please.
I just had a question. For the provable judgment, does that mean it's same as valid, and that means that all values in the formula satisfy the formula? So any combination of values.
Very good. Yeah. So
Okay.
you could write anything as a collection of proof rules, and all you're saying is that if this you follow these rules, you build something from provable formulas. You can establish provable formulas, and since you need to start somewhere, you need to start with the axioms. But you can write proof systems that aren't actually valid. So you can write proof systems that actually allow you to derive statements that may not be valid, and those would be unsound proof systems. So, for example, if I change this particular axiom, that is, instead of A implies A, I said A implies B, then you would have a problem here. So if you said A implies B as an axiom, then this would be something that isn't necessarily valid, right? You could have instances of it that is that the negation of this could easily be made satisfiable, right? You could have a situation where A is true and B is false. So if A is assigned to true and B is assigned to false, then you have a situation where you prove something that isn't valid. So you have to actually establish the soundness of the proof system as you go along.
I guess it must be quite difficult to do that for proof systems, because I guess there can be so many combinations. You have to come up with a way of dividing and I guess doing some abstraction so you can actually prove soundness easily. Otherwise, it's just too many combinations.
No, you will see that actually it's not that difficult. It's actually fairly
Oh.
straightforward to prove soundness, and we'll look at that. That's a very good point. Yeah.
So
and then you have
I have a question. Go ahead, please.
yeah.
So my question is, so in this system, we necessarily have a notion of truth that is separate from the proof system.
Yes, we do.
Okay.
Could I also ask a question? Don't really understand the second axiom. So like if A is true, then this implies that B implies A. Could you explain it a little bit? The second axiom.
Very good. Yeah. All it's really saying is that since the first axiom tells you that already A implies A.
Yeah.
So you already know that. All it's saying is that having more things out there, having adding a B to it doesn't really since A already implies A. It's saying that A and B also implies A.
Okay. So essentially, it doesn't matter which B. If A is true, like any B implies A. Is it correct?
Yeah. And actually, you're already leading into the soundness issue. You can, for example, ask yourself, is it the case that every axiom is valid? So, can you find a counter model for A implies A? Is there any truth assignment to A that would make the statement false?
No, only like if A is false.
If A is false, A implies A is true.
Oh, okay, yeah, all right.
So, there's no assignment. Either A is false and A implies A is true, or A is true and A implies A is also true.
Yeah, makes sense.
Okay. Now, take a look at the second one. So, is there any assignment under which you can falsify this?
No, not exactly. Like if A is false and B is false or true, A is still false. Yeah. Now I understand like the idea behind it.
Yeah. So if A is false, already because of this, A implies anything is true, right? If A is false. If A is true, then you have to worry about this. So the only circumstance under which you could falsify this is if A is true and B implies A is false, right? But if A is true, B implies A is true, regardless of what B is.
Yeah.
So take a look at this one. Is there any truth assignment that could falsify this?
Well, probably not, since it's an axiom.
No, I mean, but you could actually, try it out and see. So, what would happen, for example, if A were false, for instance. Okay. So if A were false, then what you have is a situation where this A implies C is always true, right?
Yeah.
So if this is always true, then this implication is also always true.
Yeah.
It's true, right? And if this is true, then this implication is also true. So we have that. Okay. On the other hand, if A is true, right, then the idea would be that we could, for example, falsify this because A is true. If C were false, for instance, that would be one way of falsifying it. If C were false, correct?
Yeah.
And so now, let's look at this situation, for instance. If C were false, then you would need to make this true, for instance, as well. You need to make this true. So the only way to make this true, if A is true and C is false, is by making B false.
Okay. Yeah. Mhm.
But if you make B false, then this becomes false. A implies B becomes false,
Mhm, mhm. Okay.
and hence this becomes true.
Yeah.
And you saw me basically kind of Sudoku my way through this. We were doing it more or less the way you would solve a Sudoku, by propagating constraints, by doing what we did in that Cheryl problem as well. Okay. Then finally, this modus ponens rule of inference says, I mean, it says
May
about
I ask
these
a
judgments.
question about, excuse me?
Please.
May I ask a question about the first line? So can you explain the first line, please, that what does it mean by provable? So does it mean specifically that so whatever you assign to any variables, A holds for any assignment of the variables? Is that true?
So yeah, the thing that these are two separate judgments. What you're talking about is A is valid, and what's being said here with this turnstile is that A is
Not this one. So the first one where you say that the basic judgment
Yeah.
here is, yeah, this one, please.
indeed, yeah. So what you're saying there is that A is provable, and these are two separate notions that you have to, as a meta logical statement, you have to establish that if a statement is valid, it's provable, and if a statement is provable, it's valid.
So my question was basically, are they equivalent? Provability and validity, are they equivalent or not?
They are different, but you can prove that they are equivalent for a specific logic. I mean, I could have written a bad logic in which they're not equivalent.
Okay. Mhm.
So provable just means it has a proof.
Okay, right. Thank you.
And if I have an unsound logic, I could prove things that, for example, are false. I could prove A and not A. Okay. Another thing that you already noticed here is that since I've stated these things in terms of A's, not P's and Q's, the A's are actually formulas in their own right. They're not propositional variables. So these are actually not axioms. They're actually axiom schemas. So if I had stated them as in terms of propositional variables, I would need to give myself a kind of rule of substitution in order to have this. I mean, although you wouldn't need that actually, you could show that you could derive such a rule. But the main thing here is that to make it kind of convenient to use, I've stated these as axiom schemas. So this is really a family of axioms, one for each A, one for each A or and B, and here one for each A, B, and C. Okay. And again, this is a family of inference rules, so that you can say, if you can prove A, and this inference rule you would have to state as a kind of schematic, so that you can say that if you have a formula A that is provable, and you have another formula of the form A implies B that's also provable, then from this you can derive B. Now, I don't ask the question about the soundness. How do you do that? We already proved that each axiom is sound. So we proved, for instance, that the first axiom is sound, the second axiom is sound, the third axiom is sound. And what you need is to show that the inference rule preserves the soundness. That is, it doesn't introduce any new unsoundness. So what it entails is showing that if the premises are valid, then the conclusion is also valid. Okay. So if these premises are valid, then the conclusion is valid. Another way to look at it is to say that if I can find a counter model of this, of the conclusion, then I can find a counter model of one of the premises. Right? That's the contrapositive.
This is, I guess, simple with a simple calculus with not many combinations. But if it's kind of a larger language, I guess there could be so many ways to put it together. So
yeah, but it's always by induction on the construction of proofs.
Right, and I guess depending on your structure, how you come up with your calculus, then maybe this will become easier.
Yeah.
Yeah.
That's right. Yeah.
Okay.
So yeah, and in general, if you have say something that falsifies B, for instance, you have a counter model for B. Okay. Then so you have this situation where B is false. So in order for this, remember this is valid, right? So if B is false, then A must be
False.
False. Okay, because that's the only circumstance under which A implies B would be valid, with B false, right? So A must be false, but A can't be false because A is valid by the induction hypothesis.
When you say you prove this usually by induction, I'm thinking like you just have all of these different transformation rules, and you're just seeing from A to B through all the combinations. I guess I don't really see how the induction works.
So my base case of the induction was that each axiom is valid. That's my base case.
Right.
Now, in any proof, the conclusion is either an axiom or it's derived from some previously proved premises using an inference rule. The only inference rule I have is modus ponens. So my induction hypothesis allows me to assume that each premise is valid. And my induction conclusion obligates me to prove that the concluding step of the proof must be valid in that case.
Yeah, and like this, it seems like a simple case. Is there an inductive step, like other kind of induction proofs, where you prove it for one, you prove it for the next, and then it works for everything?
You could do it that way too. You could actually do it that way. You could say that linearizing this proof has a kind of tree structure, right? This inference rule has a tree structure.
Yeah.
But you could linearize this. You could say that I can prove the n+1 formula in a sequence using premises that are in the preceding formulas, for instance, and then you could do strong induction to carry out this soundness proof. But you can also think of the induction as being on the size of the proof. So you could say that the size of the proof of the conclusion is at least one larger than the size of the proof of each premise of the A premise and the A implies B premise. And so by induction, the size of the proof you get.
For some reason, I thought it'd be like a combinatorial type problem where you have all the ways of putting the language together and then you do a kind of proof like that. But
no, that's the funny thing about, when you make things compositional like this, you don't have those you don't have to think about the combinations.
I see. Okay, thanks.
I just had a small question on the previous page. Can you explain what this format in point number 4 means? Like, what does this mean of writing it below? This format of writing A implies B, and B on the bottom, like what does this mean?
So what it means is that you can expect to see a something like there's a proof of A here, and there's another proof of A implies B here, and that this is an additional node in this tree. So we computer scientists, we normally write trees downwards, but this is actually an upward growing tree. But the idea is that somewhere out there you have a proof that A of A, and if you have a proof of A implies B, you can combine that into a tree that is actually a proof of B.
So it means that A and A implies B implies B. Is it something like that?
No, it's different from that actually. So it's not. You're not saying provable of A and A implies B implies B. You're saying provable of A and provable of A implies B in the meta logic implies provable of B.
Okay.
And you can use these rules to prove the formula that you just indicated. But do that as an exercise. You can do it as an exercise. Prove that A implies B
A implies B.
implies B. Okay? So you can prove
Okay.
that is
So can I ask
A implies
another
B.
question? Like probability is like
B.
similar to validity or satisfiability?
It's a judgment, yeah. But it's a syntactic judgment on these proofs rather than a semantic judgment on the kind of meanings of the formulas. So in stating this, I have not actually made any reference to meaning, right? I've not mentioned truth tables. The notion of what's an axiom is a purely syntactic constraint. The notion of what is an acceptable application of the inference rule is purely syntactic.
Mm-hmm. Okay.
Okay. So now, one important thing about the Hilbert proof system is something called the deduction theorem. So one thing I can do is that I can go back to this logic, and I can say that I want to actually write conditional proofs. I want to say that if I had other axioms beyond the ones that are listed out there, I should be able to derive something. So I want to say, for instance, that if it happened to be the case that I could prove A1 all the way to AN, then if then I can prove B, right? So that way, I'm kind of saying, supposing it were the case that something was provable, then I can prove that. So this we can actually rewrite as that. You can just rewrite that as gamma B. So you can assemble all the A into the A's into gamma and say, this is a new judgment. It's a conditional judgment. And it says if each formula in gamma were provable, then B is provable, right? And the kind of deduction theorem says that supposing if gamma comma A conditionally proves B, then gamma conditionally proves A implies B. Okay. So it allows you to basically say, instead, I'm trying to prove A implies B, but let me assume A is provable and then prove B. And that's a typical, the way you would do many proofs is when someone asks you to prove A implies B, you say, let me assume A and then prove B, right? Now, this is an exercise for you. Show that in this proof system, this theorem holds. Okay, so that the deduction theorem holds.
If you assume A, don't you have to somehow, discharge that assumption?
Yeah, you instead of discharging it, you just add it to the conclusion. So, it's because you're trying to prove A implies B. You're saying it's really okay to assume A and prove B. And once again, just as we did with the soundness proof, you can use induction on proofs to establish this.
Okay.
So you could basically look at the proof that the conditional proof that you have of B from the kind of newly added axioms gamma comma A, and show that you could actually derive a new proof in which the only assumed axioms were gamma, and instead you proved A implies B. Okay? So do that as an exercise.
Sorry, what is the main principle of induction again? Is you just assume you have one thing, and then it's just like an implication, or
Yeah, a good question. Yeah, so basically, if you want to prove, say something holds for all proofs, right? You want to prove something holds for all proofs, then you can say that so you want to prove some statement P holds for all proofs. So P of phi holds for all phi, for all phi, P of phi holds, right? So you can do this from showing that for all axioms P holds. So P of axiom, and you can say that if you have a kind of inference step from pi 1 and pi 2, then if P of pi 1 and P of pi 2 prove that P of the inference rule of pi 1 and pi 2. Okay, so that's the kind of thing you're looking at, which is that it's basically saying you can assume it of the premise proof, the proofs of the premises, and then prove that it holds of the proof that you built, adding the conclusion of the current inference rule of the inference rule you're looking at the kind of end of the proof. So that's the kind of rule you'll have to use, and if you can do that, then you prove for all pi P of pi.
all pi P of pi. So this is this like an inductive step in those numerical proofs where you?
It's very similar, yeah. So you can think of it as an induction on the sizes of the proof. So that, yeah, it's a similar thing. I mean, and so that's the principle you'll be using here.
Okay.
Okay, so so the next kind of proof system is one that takes this notion of the deduction theorem and builds it in. So it's kind of a step from the Hilbert proof system. So you can say that the basic judgment now is just the kind of conditional judgment that we had with the use of these additional axioms. So you can say gamma proves A, is just the judgment now. There's always going to be 0 or more formulas in gamma. And now the rules of inference are actually given again. All you have is implication, and the rules of inference are of this form actually. So you can say that gamma comma A proves A is a an axiom. So for any A, if you have if you're allowed to assume A, then you're allowed to derive A. The second rule is like modus ponens. It says that if gamma 1 derives A, and gamma 2 derives A implies B. Then from gamma 1 and gamma 2, you can derive B. Okay, so you have to take the union of the premises, of the kind of conditions that you're assuming, the conditional axioms. So you got to take the union of those. And this really means that, if you have two separate proofs, one is a proof of the left branch, the other is a proof of the right branch, that you're kind of merging the leaf nodes of those branches, the leaf nodes namely being those axioms that you assumed. And finally, you have the deduction theorem itself codified as an inference rule. Namely, if gamma A derives B, then gamma derives A implies B. Okay. Now, another way to look at this is that you have basically one axiom. It's saying that essentially A is stronger than A, okay? Because from A you can derive A. Okay. You have a rule here that actually says that if you have an implication above, you can eliminate it, and you can eliminate the implication by essentially clashing it against something where you've already proved the antecedent of that implication. So if you've already got A and you already got A implies B, then you can eliminate the implication and get B, right? And finally, the third rule is actually a way of introducing an implication. So it's a way of saying that if you have a B derived from and one of the assumptions is A, then you can derive A implies B. So and in terms of kind of how you view this, you're slowly moving from something where you took your initial intuition about these formulas and the connectives and their truth table interpretations and so on. You put them into some axioms and rules, and now you can just mechanically apply the rules. You don't care what the interpretations are, because all you need to do is just as we did with the task master proof. You can say, oh, every time I'm trying to prove something of this form, I can just apply this rule. So if this kind of thing isn't an axiom, that is A implies B doesn't already occur in gamma, then all I can do is actually just apply this rule of inference mechanically. I don't have to think about it, and I get this premise out of it. So you can think of building proofs from the desired conclusion upwards. And the same thing here. I mean, this requires a little more creativity. So you're staring at B, and you think, oh, it just so happens to be the case that I have an implication out here, and I can actually eliminate it. And particularly, what you can do is you can be proactive about this. You can say, oh, I applied an axiom. I got something, and the A happened to be of the form B implies C. Now, B implies C kind of matches this, and somewhere else I managed to derive in my bag of things I've already derived, judgments I've already made. I happen to have an matching A, or say this was B implies C and this was B. I happen to have a matching B out there, and from these two, I can actually eliminate that implication. So if you proved something where you have an implication, then you can look for opportunities to eliminate it.
Sorry, I have a question.
Yeah.
Why do we like to use, I guess, logic like this as opposed to trying to kind of do the same thing with computation, like lambda calculus?
I'm not exactly sure what you mean by that question, because the logic is a way of actually making claims. You have statements, and you want to be able to construct proofs of some of these statements. So the lambda calculus is a calculus for writing programs.
But they're so similar in the way that they you arrive at a conclusion, but with a calculus, lambda calculus, you arrive at some expression result. I mean, in a way, that's like a conclusion.
Actually, this is an excellent observation. So this couple of things here is actually the let's see here. Okay, so this exercise, are any of the axioms redundant? Let's see if you can prove the first axiom from the other two. Okay, so that's kind of an interesting question you might ask, right? Perhaps I don't need this axiom. We spent a lot of times the parallel postulate that Euclid had. People tried to see if you could do without it. Maybe you could derive from the other axioms. People spent centuries trying to do that. So what is actually going on is there is a correspondence between this proof system and lambda terms. So if you view this as a lambda term, it's really the kind of the type of the lambda term lambda xx. Okay, so if you look at what is the type of lambda xx, so you say lambda x of type A, okay, and x. So what is the type of this term? What input type does it take and what output type does it return?
A to A?
Yeah, so this is A arrow A, right? And that's exactly matches the A implies A.
How does
Yes?
that work? You've got a variable, lambda variable, and then the expression A dot X. What does A?
No, sorry. This is the type X of type A.
Oh, I see. Okay.
Yeah. So so you say you're binding a variable of type A, a variable X of type A, and returning X itself. So the return value it basically takes an A and returns an A. So it's of type A implies A, or A arrow A, but you can view it as A implies A. Now take a look at the next one. So what lambda term would have that type? So take a look at this one. What lambda term would have this type?
The function that takes two arguments and returns the first.
That's right. Yeah. So it's I think someone's written it already on the chat. So it's oops, sorry. Lambda x. So that should be lambda x of type A. So I'll write the type as a superscript. Lambda y of type B, and then you just return x, right? So this is something that takes A and then takes a B and then returns an A, and so it has the type A arrow B arrow A. Okay. Now let's take a look at the third one. It's more complicated. What lambda term has that type? So remember, we already saw that A arrow B arrow C is of the form lambda x lambda y something. So any lambda term, anything of that form. So if you have something of the form lambda x
Is it
of type A, I'll just write this B arrow C. Okay, you can apply it to two arguments. Okay, and then you can write the next one is going to be this particular term here. Okay, A implies B, so that's going to be lambda y, and the superscript is going to be A arrow B. Okay, then you have you had to build something of type A implies C. So how do you build something of type A implies C from X and Y? So for A implies C, you're going to take a Z of type A, right? Of type A. Okay, now you have X, Y, and Z. What can you do with these? So I need something of type C. From X, Y, and Z, give me something of type C. So can I apply X to Z?
Yes.
Can I apply X to, can I apply Y to Z?
Yes.
Okay, so if I apply X to Z, what do I get?
A function from B to C.
Yeah, and if I apply Y to Z, what do I get?
A B.
Right, now, since applying X to Z gave me a function from B to C, can I apply that to something?
You can apply it to the B you got from Y.
From applying Y to Z, right?
Mhm.
So essentially I can do X of Z applied to Y of Z. And what is the type that that returns? So X of Z is of type B arrow C, right? And Y of Z is of type B. If I apply B arrow C to B, I get
C.
C, and that's what I needed. I needed the C at the end. This C, I needed that. Okay, so then actually this rule, the modus ponens rule here, is essentially saying that if I have a lambda term of type A arrow B, I have a lambda term of type A arrow B, and I have a lambda term of type A, I can apply the first lambda term to the second to this second one, and derive something of type B, and that's just the beta reduction rule. So there you go. There is this correspondence between these two. Okay. Now, any questions on this?
Is a something like lambda x dot x the same as like a kind of a single mapping from
Lambda x dot x is the identity function
identity function? Yeah. So any x.
because it takes the x and returns it.
And I guess x can be, well, if it's typed, it's a. Would A be a set? Is it a set A?
It could be. I mean, but it's a type. I mean, you have to think about the type as the syntactic object and the set as its meaning.
Right. Syntactic object. Yeah.
So very good. I mean, you got that. There's kind of this correspondence between the formulas in this logic and types in a type lambda calculus.
Because I'm trying to think if there's like to provide implementation details where you see the actual mappings, because I guess that comes from the expression. I mean, how do you link the inputs to the outputs through the individual mappings, like the morphisms?
Yeah, you don't have to worry about all that. I mean, all of this is just syntax. Okay, the type system you're talking about is that the purely syntactic judgment saying expression E has type T is purely a syntactic judgment.
Right. So it's just kind of like a rewrite. You're having one thing and you're replacing it with another.
That's right. Yeah.
And the semantic gives it the what it means to go from one to another thing. Yeah, okay.
Yeah, so that's right. Yeah, in the semantics, you would actually have a notion of a type being a set, a type A arrow B being a kind of function space, and the idea is that you would have to show that the function you define, for example, lambda xx, its meaning in the function space behaves like the
Yeah.
identity function.
I just feel like with syntax, you can have a lot more structure that is more obvious. So like if you were able to, kind of encode the semantics inside the kind of syntactic transformation, it's kind of becomes more clear almost.
Absolutely, yeah. So this is the kind of whole point of this is that there's only so much you can do. Your intuition will only take you thus far. At some point, you got to kind of start saying that, okay, I've captured in my syntax, I've captured the semantics, and now I can do manipulation. Just like you when you think about algebraic manipulations with numbers, you don't think in terms of cows or sheep or grains of sand. You've moved on. You've just kind of said, okay, I know how to manipulate these numbers. I know kind of I'm doing the algebra correctly. And you know that the results will correspond when you actually think in terms of cows and sheep and marbles or whatever it is you want to think in terms of, right? So you want to turn things into a calculational form so that you don't have to keep referring back to the original intuitive interpretation of things.
Yeah. And is there a way to do that with lambda calculus or some kind of thing similar?
Yeah, absolutely. Yeah. So, all of this can be captured, and the type theory lectures later on today will cover this in more detail.
Okay, thank you.
So now we saw natural deduction. It again has a similar, you can give this a similar kind of lambda calculus treatment in the sense that, if you have a judgment of the form, A1, comma A2, etc., and you have B. Okay. Then what it really means is that if you have a proof of A1 and you have a proof of A2, Y, then you have some expression here that's of type B that may have X and Y as free variables.
Sorry, I had one question. Is natural deduction actually more expressive than the Hilbert system we've seen earlier? Or are
Not
they...
necessarily, yeah. So when you codify all of these things, both systems are sound and complete.
Okay, because I was thinking we could take all of these assumptions and rewrite that as, for instance, A1 implies A2 implies B and try to prove that in the Hilbert system.
Yeah, so you can actually show that any proof in the Hilbert system can be transformed to natural reduction and vice versa. Okay.
Right, thank you.
Good.
So one question, I think my understanding is that the only difference between natural deduction and Hilbert system is that in Hilbert system, you cannot start with any assumptions. They all need to be axioms.
That's right. And then you extend it with this deduction theorem because you proved that the deduction theorem was actually a theorem. And then, most people would normally use that extended version of the Hilbert system. And that's essentially natural deduction.
Okay, got it. Thank you.
Yeah. So now the picture you have of the person out there, and I think this is the only picture of anybody I have in my slides, is Gerhard Gentzen. He invented both the natural deduction calculus and what we're going to talk about now called the sequent calculus. And he actually died in World War II quite young. So he had an amazing set of accomplishments, but he probably died in his 20s in World War II. Another person that I'll mention who also, unfortunately passed away in his 20s later on is a logician by the name of Jacques Aubrun, who died in a mountaineering accident, I think when he was like 21 or something like that, but left behind, basically a book's worth of very impactful mathematics. Now, the Hilbert system extends the natural deduction's judgment of the form gamma arrow A by saying, why do we have this asymmetry between the assumptions and the conclusions? Why don't we, make them symmetrical in some sense? That is, why don't we, just as we have a set of assumptions, gamma, why don't we give ourselves a set of conclusions, delta? And now what we're saying is that these things now have a dual thing. Being on the left of the arrow is different, is dual to being on the right of the arrow. And so the interpretation you should have of this is that you're saying when you say gamma arrow delta is provable, then you're saying that the conjunction of gamma implies the disjunction of delta is valid. Actually, that's what it corresponds to when you take the semantic interpretation. So you have to now think in terms of, gamma being essentially, say of the form A1, A2, A3 as being A1 and A2 and A3. So the comma on the left will mean and if delta is of the form B1, B2, B3, you have to think of it as B1 or B2 or B3. Okay. So remember that when you're interpreting the rules. And note in particular that so when you have something, for example, A implies B or C. Okay. So you can turn that into A implies not B implies C. Because B, remember, not B implies C is the same as not B or C, which is the same as B or C. So you can think of that as, A and not B implies C. So the interpretation of A implies B or C is the same as A and not B implies C. And roughly what that means is that if you're trying to prove something of the form B or C, it's actually fair game to assume not B and then try to prove C from that. Okay, so with that in mind, let's interpret these rules. Let's examine these rules. So the first rule is similar to the axiom rule of natural reduction. It says that if you have an A on the left, that implies an A on the right, regardless of delta. And the reason that's reasonable is that, remember, it's, you have to think of this right occurrence of A as A or delta, right? So what it's saying is that from gamma comma A, you can prove A, but you can prove A or anything else, any A or delta, because A or delta is strictly weaker than A. It's like the Linda problem. So that's the reason the axiom makes sense out there. So then the rules break down into a very nice symmetry of left and right rules. So in the sequent calculus, all you have are these introduction rules for each connector, but you have left introduction rules and right introduction rules. And you can think of, roughly speaking, the left introduction rules correspond to the elimination rules of the natural deduction calculus, and the right introduction rules correspond to the introduction rules because you're introducing a connector into the conclusion. Okay, so here you have the first rule is the one involving negation. And I already kind of gave you a little bit of an explanation of how this follows. So, if you're trying to prove from gamma, you're trying to prove A or delta. I'm sorry, this way. You have to read it the other way, from conclusion upwards. So if from gamma and not A, you're trying to prove delta, then, it's the same as trying to prove, you might instead try to prove A or delta from gamma. Because here the interpretation is that it's not A implies delta, and not A implies delta is the same as A or delta, and so that's, you're trying to prove A or delta. Okay. So then here you have the situation where you're trying to prove from gamma not A or delta, and not A or delta we saw was the same as A implies delta, and that's what this is. You're saying from gamma you're trying to A implies delta.
When you say or, I thought the comma means and usually. Huh?
No, the comma on the right means it or.
It's always
comma on the left
okay.
means and.
Oh, I see. According to that.
Yeah.
Oh, yes. Yeah.
Okay. So good. And do the negation rules make sense to you? So remember, there's a left negation rule, and there's a right negation rule. both introduce negation into the things below the line. Okay, and in a sequent, we call the kind of gamma part of the sequent the antecedent formulas, and we call the delta part of the sequent consequent formulas, sometimes succedent formulas, but antecedent and consequent. Okay, and remember, it's the conjunction of antecedents implies the disjunction of consequent. Okay, so that brings us to the disjunction rule, and it's easiest to actually start with the right disjunction rule. And here, since the comma on the right means disjunction anyway, it means or anyway. So all you need to do is replace this or here with a comma. Okay, that's all you need to do. Okay, and you can move on. The one on the left is actually quite an interesting rule. So what it has is that you have a left antecedent formula of the form A or B. Now you can't replace that with a comma clearly, because that would turn A or B into A and B, and that's cheating. I mean, all you were allowed to use is A or B, and A and B is a much stronger claim, a premise to work with than A and B, A or B. So that's why you want to be careful how you use this. But on the other hand, what you can do is you can say, okay, I'm trying to prove A or B implies delta. From gamma, I'm trying to prove A or B implies delta. How would you do such a proof?
Consider the two subcases where one where A holds and the other one where B holds.
That's right, yeah. So, this is a typical thing that you do. You say the natural numbers are either odd or even, okay? And so you can do a proof for the odd case and you can do a proof for the even case. Exactly, that's what's going on here. You're saying that you do one branch of the proof with the antecedent A, and you do another branch of the proof with the antecedent B. And if you have those proofs, then you can conclude that from A or B, you can derive delta.
So
again, a left rule for OR and a right rule for OR.
Yes. One question is, in the OR rule, in the antecedent, is it the case that we say A is an assumption and that proves delta, and B is as an assumption and that proves delta at the same time? So isn't that stronger than we are saying A or B can either proves, like, doesn't it become AND rather than OR?
No, not on the left. So
Okay.
on the right, that is true. So it is the case that becomes an AND. But on the left, you're saying that I have one proof in which I can assume A and prove delta. I have another proof in which I can assume B and prove delta. Okay. Now, from that, I can conclude that I can assume A or B, and in either case, if it's the A case, I can prove delta. I can prove in the B case, I can also prove delta. So from A or B, I can prove delta.
Okay.
So just thinking about this like general structure, it seems to always branch outwards. I mean, I'm thinking like math functions. For it to be a function, you have like many to one, whereas this seems like it's going from one to many, because you have ANDed terms, and then on the other side you have disjunctions.
Yeah, so it's a branching proof structure. All of these systems that we saw have two premise rules. That is, they have one conclusion judgment that can actually split into two premise judgments. So you're
Isn't
actually
it easier to
building
think? Isn't it easier to kind of reduce? So you're coming from maybe more to few.
You could do that if you want. I mean, you could say that you're always working with a set of judgments, that you're always looking at say the kind of a set of leaf nodes in a proof, and you always go from a set of these to a set of these if you want to kind of sequentialize it.
Okay,
So that can be done if you want.
thanks.
So the AND rules are actually dual to the OR rules. So what you see happening on the left with the AND happens on the right with the OR, and vice versa. So that means that these two are kind of similar to each other, and these two are similar to each other. So the left AND rule is easiest to see because we saw AND on the left was already the comma on the left was already conjunction. So you can replace A and B by A comma B. And this is actually roughly similar to what we saw with natural deduction, where you were writing A implies B implies C, or A and B implies C. And so what you've done is you've just turned an A and B implies delta into an A implies B implies delta. Okay, that's kind of what you see happening out there. So that's just replacing AND with conjunction. I mean, comma, replacing AND with comma. The right rule is more challenging. So the idea here is that from gamma, you're trying to derive A and B or delta. So, if I told you to prove A and B, how would you typically go about proving it? So how would you typically go about proving A and B?
You first prove A and then B.
Yeah, that's it. You separately prove A and you prove B. Okay, that's exactly what's captured in this right rule for the conjunction. Okay, so it's similar, very similar to the kind of case analysis of these are actually duals of each other. And it's really important to appreciate the duality of it, because then you have to only remember one side of these things, and you can figure out what the other one should look like. So the duality splits halves what you need to remember. Then we come to the implication rule, and again the right implication rule is easiest to understand because the turnstile symbol here, this turnstile symbol represents implication. So if from gamma you're trying to prove A implies B, so just as we did with the deduction theorem, you can say, okay, I can just do derive B from gamma comma A, and I'm done. Okay. So this is again a very typical thing. It corresponds to the flatten step in PVS. So when you do flatten, it actually applies. Flatten basically applies all of the one premise rules out here. All of the single premise rules are handled by flatten in PVS, and the two premise rules are handled by split. Okay, now the left implication rule is a little more challenging again. So if I told you to prove, derive B from, derive C from A implies B, how would you do it? So you can think of the A implies B as a lemma. And how would you use a lemma?
That's not of
The hypothesis, then use the result, the conclusions, and then prove the hypothesis.
Precisely, yeah, that's right. So that's what's going on out here. You're saying that I have this lemma A implies B, and what I can do is I can use the B in deriving delta, provided I've discharged the A. So as long as I can discharge the A, I can use the B. Okay, and that's what the implication rule is.
What is the meaning of discharge?
Oh, that is, this you can think of as you're allowed to use B, provided you discharge A. Discharge means you're proving it as a proof obligation. Yeah.
Okay.
And finally, we come to the cut rule, which is quite important. So it's again in some ways dual to the axiom rule out here. The axiom rule says the left A is stronger than the right A, and this one says basically, well, the right A is stronger than the left A as well. So what it's saying is that you're trying to prove some sequence to the form gamma arrow delta, and you're allowed to kind of essentially introduce a new lemma of the form A in trying to prove gamma arrow delta, provided you discharge the A. So if you prove it on one branch, then you can use it on the other branch, essentially. And the advantage of this is that, A here might be a useful lemma that you might want to use multiple times in a proof, but you only want to prove it once. You want to prove it once, as a lemma, and then use it multiple times. I already, yesterday talked about how a lemma is a labor-saving device because you prove it once and use it countless times. So that's what's going on out here. So this proof you do once. This kind of use of the A you might do many, many times. So the cut rule is actually something that compresses the proofs in a way that's kind of super exponential. Actually, is it? No, it's I think super exponential. I forget. So it really does compress the proof. Okay, so the cut rule is actually something that is admissible. Okay. And I missed this thing actually. I forgot to mention here the distinction between a derived rule and an admissible rule. Okay. So the the idea of a derived rule is that it's saying that you can actually get an inference of this form. That is, you can actually create a compound inference where from the premises P1 and Pn you can kind of get C. Okay, so that's a kind of derived rule of inference. The admissible rule of inference is a stronger thing. It says that you can only do this by claiming that P1 to Pn are provable. Okay, so it's important that they be provable, and that makes quite a bit of difference because in a derived rule, it's actually not requiring that. It's not requiring that the P1 Pn be provable. That is, you don't have to have a proof of it. Okay.
Why would you want to use the derived version?
Why would you want to do derived?
Yeah.
Yeah, because it's very convenient. I mean, you typically only use it in situations where you have a proof of it. But like the deduction theorem here, I'm not insisting that well, here I am actually. So here I'm saying that if this is provable, then this is provable. Okay. So it really depends on the provability of this. So it's like an admissible rule. But you might just want to have a shortcut. You might want to take a bunch of inference rules and compress them into one inference rule, and that's why you would need a derived rule. So every derived rule is admissible, okay, but not vice versa. And in particular, I think the example of this is actually the deduction theorem, not a derived rule. Okay, so the cut is actually eliminable. That is, it's an admissible rule. You don't need it. But if you eliminate the cut, you get much larger proofs. Okay, so here's the Peirce's formula. You can try this particular formula. You can try to prove it in many different systems. So here you can see how in the sequent calculus, it's again a mechanical application of the rules. Every time you see something that's a connective on the right, you split it with the corresponding rule. If you see it on the left, you split it with that corresponding rule. So here you see that you have this P implies Q, whole implies P, whole implies P. So the obvious thing to do is what? Which rule would you apply to this conclusion?
The implication rule.
The right implication rule, yeah.
Right.
So the right implication rule just moves this stuff to the left of the turnstile. So that's what you see out here. So you see that move here. Okay. Now you have this sequent. So what would you apply here?
the left implication rule?
Yeah. So again, all of this is turning mechanical, right? So you apply the left implication rule. So on this branch, you do that P implies P. So you use the conclusion here. And here you have to discharge the P implies Q. That just moves to the right. Okay, you have to discharge it. So we are applying the left implication rule to derive that. And now how would you deal with this?
Right implication.
Absolutely. So you apply right implication, you get something of this form. Okay, you get the P moves to the left of the arrow, and you're left with P comma Q, and that's an axiom, and you're done.
Oh, I had a question. Shouldn't we also have a rule that allows us to add any assumptions to a formula that we know is provable? Like if we have a P entails Q, could we produce P comma P1 entails Q?
Yeah. So what has happened there is that you've actually kind of moved all those kind of what are called weakening steps. So if you have something of the form P implies Q, and or P turnstile Q, right? I mean, that would be a good example. P turnstile Q, and you want to actually say that, okay, from that I can also prove P comma R turnstile Q. So all those weakening steps have actually moved to the axioms. So here, essentially, you can throw in whatever you want in the gammas and deltas, and just carry them around as baggage. So all weakening now has moved to the leaves. Let's say, does that answer your question?
But in that rule, we have A on both sides. I was thinking more about something that would look like.
Yeah, actually, your rule, the rule you want, would be derivable from this. So if you can, if you have a proof, what I do is I just kind of throw in the extra baggage into it, and it just gets carried all the way down from the axioms to the conclusion.
Okay.
Okay. So
thank you.
Okay, so let's skip some of these things. And now, we'll talk a little bit about kind of the automation of propositional logic. Now, the things you can do with a Boolean formula, okay, you can check satisfiability, you can check validity, but it's not effective to kind of claim something as valid by means of checking validity all the time. But you could, for instance, build proofs for it as you wanted. But you could actually start looking at maybe checking validity is an efficient thing to do, and perhaps build a satisfiability solver for it. So as a step towards building a satisfiability solver, so the way you'd use a satisfiability solver to check validity is you'd throw it the negation of the formula. If the negation of the formula is satisfiable, you have a counterexample to your original claim. Otherwise, if it's unsatisfiable, you know that the original claim is valid. So a formula is in negation normal form if negation is never applied to a compound formula. It's only applied to propositional variables. So again, as an exercise, show that you can take any formula and turn it into a negation normal form formula. Right? The negation is at the variables. It's at the leaves. So you'll never see something of the form not A and B or not A or B. And the De Morgan rules actually tell you how to distribute that, and you just apply the De Morgan rules successively. You build a negation normal form. Now, in a negation normal form formula, you have propositional atoms P, or you have the negated atoms not P. Okay, so you have these two kinds of things, and you call those literals. So anything, a literal L is anything of the form P or of the form not P. And clause is going to be this n-ary disjunction of literals. It's going to be L1 or L2 or L3. So something of the form not P or Q or not R is a clause. Right? So it basically says these are the only possibilities. So that's what the disjunction captures. And then you can basically build up a clause set as a conjunction of individual clauses. So if you have clauses, here it's a multi-array conjunction, but if you have clauses K1, K2, K3 up to Km, then you can think of the conjunctive normal form as a conjunction of clauses. Again, as an exercise, you can show that any Boolean formula can be turned into a formula in conjunctive normal form, which also happens to be in negation normal form. Okay? So that means you can basically think of it as a conjunction of disjunctions. That's all you need. It's a two-level formula. You took out all the nesting that you had and just said it's a conjunction or disjunction of literals. So that's what this conjunctive normal form is. So here's an example of a conjunctive normal form. So it's the first line is a disjunction of literals, not P or Q or not R. The second line is disjunction P or R. And the third line is not P or not Q or R. Okay, so kind of define these things so that you can get and show that any Boolean formula can be turned into a CNF formula where you have at most 3 variables per clause. So this is a 3 CNF formula, for instance, because it has at most 3 variables per clause. Okay, so I'll skip the soundness thing. You can do that as an exercise. I'll skip this. I'll skip interpolation as well. So now let's talk about resolution. So here, what we're doing is we're saying, okay, I'm going to give you a set of clauses, and you have to demonstrate to me that this set of clauses is unsatisfiable, or you might fail to do it. Okay? That's the proof system in some sense. It's a mechanical proof system, but it's a proof system where you want to demonstrate the unsatisfiability of a formula in CNF. So now, I can think of a formula in CNF as a set of clauses. Right? I can take the set that I had there here, and I can take the formula that I have there and just say it's a set of this clause and this clause and the third clause here. So those are the set of clauses that I'm working with. Now, what you do with those set of clauses is that lurking in them might be some tautologies. You might have something of the form not P or P. Okay? The problem with something of the form not P or P is what? So if you have a set of clauses K1, K2, K3, and K1 is at the form not P or Q, not P or P, what can you say about it?
It means that
True.
clause doesn't
The
matter.
tautology.
Yeah, so it contributes nothing. It's it's a zero constraint on the thing. You may as well just drop it, right? Because every truth assignment satisfies it. What you want are clauses that are genuinely at least eliminating one truth assignment, right? So this is not an interesting one. And if you drop it, the resulting set of clauses is equi-satisfiable. Do you agree?
Yes.
So if K is satisfiable, then K together with not P or P is satisfiable. Because after all, in the satisfying assignment, P must have had a truth assignment true or a truth assignment false. Either way, it's satisfiable. And vice versa. If K with not P or P is satisfiable, then K is also satisfiable, right? So that's the reason you can actually drop it, because if K with anything else is satisfiable, K is already satisfiable. So that's a kind of trivial case. Okay, so now you've eliminated these tautologies. So you have these set of clauses. So you can now start applying certain rules to it. So what you can do is you can say, if I have two clauses where one disjunct L occurs in one clause, so L occurs together with say some other disjunction gamma 1, and in the other clause I have not L, the complement of L, occurring with gamma 2. Then what I can do is I can actually resolve the L against the not L and just derive a new clause, gamma 1 or gamma 2. So I can derive this new clause, gamma 1 or gamma 2. Okay. And once again, I want you to kind of check that this clause set above the line is equisatisfiable with this clause set below the line. So you need to check that to make sure that I'm not creating any new assignments or losing any assignments. Every truth assignment for the formula above the line, okay, it can be extended or serves as a truth assignment for the formula below the line, and vice versa. Now, as you do these things, as you keep resolving, you might end up with these unit clauses. You might end up with a unit clause L and another unit clause not L. And since the interpretation of the set of clauses is conjunction, I cannot simultaneously satisfy two clauses, one of which is L and the other is not L, right? And that's when I signal unsatisfiability. I say, the clause set is unsatisfiable. And bottom indicates that, right? So let's look at an example of this. Oh, it's important to note the side condition that you always add a new clause, not one that's already in there. And you make sure that you don't apply the rule when gamma 1 or gamma 2 could become tautological. Okay, so let's look at an example of this. And so here I have the clause set of this form, not P or not Q or R, not P or Q, P or R, and not R. Okay, so the first kind of resolution step that I do is, I resolve not P or not Q or R against P or R. Okay, and so I get the new clause not Q or R. I mean, actually, I get not Q or R or R, but it's redundant to say R or R. R or R is the same as R. So I just reduce that as not Q or R. Good. Okay. Then I can resolve these two. I can resolve these two, not P or Q against P or R. Okay. And I get Q or R. Now I can resolve these two because it's got not Q in one and Q in the other, and I get R. And now I have two unit clauses, not R and R, and I get bottom. So the initial clause set is unsatisfiable. Now this it wasn't obvious to me that this is unsatisfiable, but applying these rules now makes it so that you can see that it is indeed unsatisfiable. Are we good? Okay, so we'll pause here, but there's one thing that I actually do want to note, which is that in applying this resolution rule, you only need to look at, so you can for example order the literals in a clause, and you can apply the resolution step to only the head literal in the clause. You don't need to apply it to any other literals. So out here, that's what I've done. So I've made it so that the P always appears before Q, always appears before R, and I've never resolved on any literals that aren't the head literals of their clauses. So I always resolve, not P against P when both are head literals. So I could have, for example, resolved not P or not Q or R against not P or Q, but I did not do that. And even though I chose not to do that, I was sacrificing the opportunity to do that, the system is still sound and complete. Okay, so you don't lose any demonstrations of unsatisfiability in spite of this, let's just resolve on head literals constraint. Okay, so that's something that you can look at and prove on your own, why that's true. But it's kind of interesting now when you mechanize this, that gives you a huge efficiency boost, because now you have so much such a smaller scope for non-determinism. You only have to look at the head literals and resolve against them. You can employ efficient data structures for indexing them, and so you can kind of mechanize these things very efficiently, knowing these kinds of constraints. Okay, so with this, I'll pause now and take some questions for a few minutes, and then turn off the recording, and then we'll take a break. Questions?
I have a question about resolution. So does this technique work for every logic systems?
No, so this isn't, I mean, it works for essentially classical first order logic, and you can actually extend it to some other logics, but for example, it doesn't work with constructor logic.
Okay. And another question is, can you give a historical context about the three logic system we mentioned today? Like, what is the motivation of all these three logic systems? Why do they come up with different formulation that are like already sound and complete, that already works, right?
Yeah, so the Hilbert systems were kind of created to capture what they felt mathematicians were doing. That is, they were going from provability judgments of individual formulas to provability judgments. And Jensen, I think, was actually Hilbert's student. And he was interested in, the Hilbert program was actually trying to show that these proof systems were consistent, that you could never derive 0 equals 1. And so mathematics was on a strong foundation. And so they needed systems on which you could actually do meta-mathematical proofs more elegantly. And so the natural deduction and the sequent calculus were created for that. And it is indeed the case that many meta-mathematical theorems actually are more easily done with these. But then they turned out to be nice systems to actually use as well. So PVS is, for example, based on the sequent calculus, and it works out very nicely because the big advantage of a sequent is that it is completely informative. That is, there's no context. All of the information you need is staring right back at you in the sequence. And so, any decision that you need to make is not hidden in some context. Now, there are sequent representations of natural deduction that have the same kind of property. That is, you write the natural deduction claims as gamma arrow A, so it has that property. But having this single conclusion is really unnatural when you're doing proofs. It's really nice to have the symmetry of gamma arrow delta in building proofs. So you'll see this is really a huge convenience when you're doing previous proofs, is having the full sequence right there.
How do you capture actual context of the data these judgments are on? So like, I guess, type information in these, or is that?
So those, that's also, in some sense, that's a kind of implicit part of the sequence. The type information is an implicit part of the sequence. And in an interesting thing in PVS, for instance, is that when you're looking at something of the form A implies B, you're actually showing that B is type correct in the context of A. So that's an important kind of additional power to have, which is that you can say, for instance, that x not equals y implies x plus y divided by x minus y has some property. And because if x is not equal to y, then x minus y can't be equal to 0. And division requires for its type that the denominator is non-zero. And you can prove it in the context of its use. So the type information is kind of used in this kind of contextual way, so that you can prove, in A implies B, you can prove B to be type correct in the context of A.
How would you actually provide, make it explicit? I mean, you just write it down in English, or is there like a notation for it? Or
so the proof rules actually do make it explicit by carrying around typing information. So if you look at the PVS semantics, it shows you how to do that. And in the when you hit it with the PVS formula, the PVS type checker, you see that it generates proof obligations that capture the context. So when you see something of the form A implies B, the proof obligations for B have A as a assumption.
Oh, so do they exist as just separate propositions? They're not kind of combined in any way, or because I guess you
Yeah,
can
the
have.
proof obligations are separate propositions. That's right. Yeah, they are things that you prove separately. And one of the advantages in PVS is that you can kind of go ahead and ignore the proof obligations if you want and continue with using your definitions and theorems. But eventually, you can do something called a proof chain analysis to see if there are any dependencies that you haven't fully discharged. So you had a proof obligation of a theorem that you proved, but you hadn't proved the proof obligation. And the proof chain analysis will indicate to you that you missed something. But I actually find it useful to look at at least examine the proof obligations, because a lot of times there are errors lurking in the work you've done, and the proof obligations give you this. If you try any exercise, you'll get these off by one errors. Should it be k minus 1 or k plus 1? And do I have an array out of bounds access? Am I taking the square root of a negative number? Am I misapplying a certain operation outside of its domain? So all of these are very, very, very common mistakes in mathematics that even perfectly distinguished mathematicians make. And to have something that catches you out, you should pay attention to it. So you should pay attention. That's actually where you might find these things annoying, but they're not. They're the most valuable thing that you get out of this system.
I feel like if the propositions themselves contained the actual, I guess, like structure, so you wouldn't have it separate. It might be easier rather than having like a separate notion of the data type structure and then some judgment on it. Would you not want just an expression that is the structure and is also, because the structure is itself something that can be used as a proposition. So I guess it becomes like more spatial.
I'm not sure I exactly understand what we're trying to say there, but the nice thing about making something an independent proposition is that it can be reused elsewhere. So often you find that PVS detects that it's already generated a proof obligation, the same proof obligation elsewhere, and so you can actually then just reuse it instead of regenerating it each time. So that's the advantage that you get when you,
for instance, if these symbols, because I like obviously the structure of the proof. Everything's hierarchical. You can use these sequence, but I'm thinking, can you make let's say the symbols themselves were actually like set theory, then the symbols themselves would be directly linking to spatial things, and then it would be quite obvious what things are. So then everything is in one place, and then you have all the information you need to understand. It basically just, I just feel like it makes things more like linear and spatial. If
so these are, I mean, once you get used to them, you start to gain a kind of spatial intuition about these proof rules. So you will see as you kind of get adept at using them that you start having a certain spatial intuition about them, and that actually makes things a lot more calculational for you. So you can actually then start building proofs on autopilot, and we'll actually maybe look at some examples.
Okay.
John, you have a question?
Yes. So I'm confused about this KI equals notation. What does it mean?
Oh, sorry. Yeah, that's confusing. I'm sorry that. I'm just saying that this set of clauses I'm going to call K naught. The first line I'm going to call K naught, and I'm just kind of adding to them. I'm accumulating clauses here. I don't want to repeat them each time.
So resolution is not. It's not replacing clauses. It adds new clauses.
Correct. It's just kind of you have a kind of set of these clauses, and you keep adding new ones. Yeah.
Okay. Thank you.
Yeah. Okay, let's take a break and come back on the hour. We'll take a 20-minute break or 18-minute break and come back on the hour. I'm going to pause the recording at this point. Okay, so we in the previous session we looked at resolution as a way of demonstrating the unsatisfiability of an input set of clauses. And one interesting thing here is that you also kind of as a consequence you can also get a demonstration when resolution fails to establish bottom at the end that the original input set of clauses is satisfiable. And to do that, take a look at what would happen if you took this not R and dropped it from the clause set initially. Then the rest of the clause set is actually satisfiable, and you can show that you would fail to derive bottom, and from that you can actually think of how you might reconstruct a satisfying assignment for the original set of clauses. So next we'll skip to a different way of doing a demonstration of satisfiability called CDCL. So it's conflict-driven clause learning, and it's in some sense dual to resolution, in that resolution is trying to demonstrate that the input clause set is unsatisfiable, and if it succeeds, it derives bottom. If it fails, it means that the clause set is satisfiable. CDCL, on the other hand, is actually trying to construct a satisfying truth assignment for the input set of clauses. And if it succeeds, it's got a satisfying assignment. And if it's, all its attempts at building a satisfying assignment have failed, then it, means that the original input clause set is unsatisfiable. Now, ignore all of this, and we'll actually skip to just an example. You don't need to worry about any of this things. But the main thing to know from this is that just as Aaron was pointing out, you have some set of clauses that you're working with, okay, or a state that you're working with, and you have a kind of machine that is driving you from one state to the next, and your state, is something abstract, but it has an interpretation as a formula, and literally you're driving it from one formula to another formula to another formula, all the time preserving satisfiability. So you're doing these equi-satisfiable transformations on your state. And eventually you arrive at a state perhaps that is manifestly unsatisfiable. And because you're doing this in satisfiability preserving steps, you know that the original input set of clauses must be unsatisfiable. If you fail, that is, you reach a canonical state that isn't manifestly satisfiable, then it's in a normal form for which you could actually give it an assignment. So you can read off an assignment, and then you're able to propagate that assignment back to the original input set of clauses. So that's all it is. So an inference system consists of an abstract state that can be interpreted as a formula. Each reduction step on the inference state is satisfiability preserving on its interpretation as a formula. And eventually you're going to reach either a manifestly unsatisfiable state, call it bottom, in which case your input was unsatisfiable, or you'll reach a canonical state that isn't manifestly satisfiable. And because of its canonical nature, you will be able to construct a satisfying assignment for it. So let's look at this example as our CDCL instance. So, it's just some long set of clauses, and we don't know whether it's satisfiable or unsatisfiable. So what you try to do in CDCL is that you start guessing an assignment. Now, the first step is actually you look at it to see if perhaps some assignments are already explicitly given to you in the form of unit clauses. Now, does this input set have any unit clauses in it? Anyone? Yes or no?
There aren't any.
Yeah, so no unit clauses at all. So there's nothing for me to actually conclude at level 0. At level 0 is where I can say that, independent of any assumptions, a certain literal has a given truth value. So that's not the case. So what I do is I go to level 1 by guessing an assignment. That is, I select a literal. In this case, I happen to have selected S, which isn't an inspired choice, but we can do things badly here. So I pick S as something, and I say let S be true out here. So, and I mark it as levels 1 because I'm depending on one guessed assignment. Now, supposing I make S true, does anything else turn into a unit clause?
No.
No, because making S true here just means this clause is satisfiable. So I can discard it. It's got no further role to play. I already made it satisfiable. It's got no further role to play. This one is interesting because guessing S to be true here means I make S false in this, which means that given S being true, P or not Q should be satisfied. I mean, I need to satisfy it. So, but that's not a unit clause. So I can't actually derive any unit clauses. So I give up on propagating any information at this point, and I move to level 2. And at this point, I make another guess, which is R. I say, let's make R true. Now, when I make R true, do I get any propagation out of it? Are there any unit clauses that follow from making R true?
Not P.
So
I guess there is. If R is
making
true,
R
then
true,
the
R
last
true doesn't make
clause.
not be true. It just means this clause is satisfied, and I don't need to worry about it.
The last clause makes negative Q must be true.
That's right. Yeah, making R true means that whatever truth assignment I have that satisfies the set of clauses better satisfy not Q. Right? Any satisfying assignment in which R is true requires not Q to be true, is what that clause says. So I make note of that. So I say that at level 2, I have derived or propagated a new literal not Q, and I record why I derived it. I say that it's because the input, the clause set contained not Q or not R. So I keep track of that. Now, knowing not Q, can I derive any new unit literals? Can I derive any new truth assignments? Go ahead.
Yeah, from the first one, we can derive P.
That's right. So, if I make not Q true, then, Q is false. And so any satisfying assignment better make P true. So I can derive P and I record that P or Q gave me that. Okay. Now I have this thing where I'm assuming S to be true. I'm assuming R to be true. And given those two assumptions, I've derived not Q and P. What happens now? Can I continue this into a satisfying assignment for the input?
No, with
I
a
guess
clause.
it's a conflict. Second clause.
With the second clause, that's right, yeah. So not P or Q gives me a problem because with what I have, it's completely false. Now, this isn't a disaster because it depends on assuming S to be true and R to be true. So it's not the case that we at this point can conclude that the input clause set is unsatisfiable. But it does mean that I need to back off one of those two assumptions. I need to back off of those. That is because making S true and R true is not going to be something you can extend into a satisfying truth assignment for the input set of clauses. So record this conflict, right? You have not P or Q. And remember this line and we go to the next page. So you have this conflict with not P or not Q. This is the conflict that was created. Okay. So if you look at the kind of, if you analyze the conflict, you look at what actually went wrong, you will see that if you take the P here, and because making P falsified something, and because you derived P by falsifying Q out here, you got P or Q here, it means that you should be able to resolve these two. That is, you should be able to resolve P or Q with the conflict that you had. So if you take any literal here and it was falsified, there's a justification for it in which that literal occurs positively. So that's a candidate that you could actually resolve. So you can resolve P or Q against not P or Q. What do you get when you do that?
Okay, Q.
Yeah, you get Q. Yeah. So this means that in some sense the input clauses actually allow you to derive this kind of the Q as a lemma, as a lemma. So what you can do with this is that when you have a clause of this form, where you have basically that is there's only one variable in it that was either assumed or derived at the current decision level, as Q was, and the rest of the clause is actually at a smaller decision level. That is, its variables were actually derived at truth values. They were falsified at a smaller decision level. Then you can back jump to the decision level of the rest of the clause. Now, with a thing like Q, is there a rest of the clause? There isn't. The rest of the clause is empty. So what this allows you to do is back jump to level 0 and say that I derived Q at level 0. And the reason for that is that your conflict clause at any point is genuinely a consequence of your inputs. And you only need to back jump to the level where the rest of the clause was falsified, because that means that you have a propagation step available to you. So in this case, that rest of the clause is empty. You can back jump to level 0. You can say I've derived Q. You can add it as a new clause, a learned clause. You've learned this new clause. And because you've learned it, you can then propagate it, because now your clause set is augmented with Q. You have a propagation. You say I derived Q from Q. Now at level 0, that means under no assumptions. So now that you have Q, what unit clauses can you further derive? So you look at clauses where Q occurs negatively, right? And what do you find?
P.
You can derive P from P or not Q, because any truth assignment is going to have to make Q true. If you make Q true, you make not Q false. Any truth assignment is going to have to make P false, because you have P or not Q. Okay, so you have to derive this. Now, once you have derived P, and so you record this as a justification. Once you derive P, what else can you derive?
You can derive R from not P or R.
Yeah, that's right. So from
But this is like a problem, right? Because then like you can also derive not Q from not Q or R, or not R.
That's right. we do have a problem, because now you have a clause that's falsified. And the point here is that it's falsified at level 0. Level 0 had no assumptions. You had not selected anything like you had with S and R at level 2. So level 0 has 0 assumptions. Everything in level 0 is a consequence of the input. So that means from your input, by resolution steps, you could derive Q, you could derive P, you could derive R. And if you could do that, you could, essentially resolve R against not Q or R, or not R, and get not Q. You could resolve Q against not Q and get bottom. So that meant you really found a conflict at level 0. The input must be unsatisfiable, because you did this, every step here was satisfiability preserving. At every point, what I had in K union C, if from K and C I derived, my state consists of this H, M, K, C. If I derived K prime union C prime from K union C, it meant that these two sets, K union C and K prime union C, were equisatisfiable. So in particular, if the final state is unsatisfiable, then the original input state must have also been unsatisfiable. Okay, so this is a nice kind of clean, simple way to think about what you're doing when you do inference. So when you might remember that when you were solving equations, you were transforming the input equation in stages that preserved exactly the solutions. That is, you didn't add any new solutions that weren't there in the input. You didn't eliminate any solutions that were, that were allowed by the input. So that's what you're doing here. So you can think of a satisfying truth assignment as a solution to a constraint, and you're taking transformation steps that are solution preserving. I'm sorry, I didn't have the video going. Okay, so that's the CDCL. So you can try and prove that CDCL is sound and complete. And now with the framework that I've given you, this is actually trivial to do, because all you have to do is show that the inference system in terms of these reduction steps is conservative, is conservative, progressive, and canonizing. So it's conservative because the reduction steps preserve satisfiability. It's progressive because at every step you need to show that you've reduced a state to a smaller state, something that's actually in some well-founded order smaller. So that means you cannot make infinite sequences of reductions on them. And for CDCL, that proof obligation is actually quite tricky. And in particular, the back jumping step is the one that's the trickiest to show. Why is it that, having basically, throwing away all this work that you did still somehow preserves termination? How is it that you don't cycle? And the reason you don't cycle is that every time you do a back jump step, you actually, gain some information. You gain a kind of a learned thing. You're able to make from that an inference of a unit literal at a smaller decision level. So as long as you assign greater weight to learned literals at smaller decision levels, you will, eventually be moving more and more literals to smaller and smaller decision levels. And the best you can do is get all the literals at decision level 0. And that's why it eventually converges. The final step is, why is it canonizing, which is that either it's manifestly unsatisfiable, that is, you hit a conflict at level 0, like here, you hit a conflict at level 0, or you did actually, you didn't hit a conflict, and you were able to actually make a truth assignment that made every formula in your input true. Yeah, because that's what the absence of a conflict means. So you were able to, essentially give every one of these a truth assignment. It could have been a truth assignment at decision level 23. But at any rate, as long as you don't hit a conflict with that truth assignment, it means you satisfied every input clause, and hence, you're done. Any questions on this?
How would this be related to something like DPLL? Is DPLL just an implementation like the algorithm, or is that sort of different than what CDCL is trying to do?
Good question. So, DPLL is a somewhat more naive version of this. So in DPLL, you do have the selection and unit propagation steps, and you do hit a conflict, but you don't do any conflict-driven clause learning. So you don't learn any new clauses.
Okay, thank you.
So the DPL stands for Davis, Putnam, Logum, and Loveland. And essentially, Davis and Putnam had a method that they created in 1960. And that it also had a resolution rule in it. And when Davis, Putnam, Logeman and Loveland started implementing it in around 1962, I think, they realized that they didn't need the resolution rule, and they threw it out and kept the others. So that's DPLL. And an interesting story about this is that in like 1963 or so, I think, Alan Robinson was a professor, a logician at Rice University, and he went to Argonne National Labs to spend a summer. And the head of the mathematics division at Argonne National Labs was a person by the name of William Miller. So later on, actually, when I joined SRI, William Miller was the president of SRI, the president and CEO of SRI. And he was also a professor at Stanford. But when Alan Robinson went to Argonne National Labs, Bill Miller gave him a copy of Davis and Putnam's paper and said, I think you can do something with this. And Alan Robinson came up with the resolution rule. That is, it's a rule that you use in first order logic. That is the basis of many automated theorem provers today. He came up with that in 1963 as a result of this inspired suggestion from Professor William Miller. Okay, so I'm going to skip BDDs for now and move into first order logic. Okay. Now, we've remember that in propositional logic, you had propositional variables, you had negation, disjunction, and conjunction. And we're going to kind of get to first order logic in small steps. The first step is one where we allow ourselves some constants, basically. So, you give yourself some constants, C1, C0, C3, and so on. And the reason for this is that in propositions, you can only talk about conditions that hold. You can say, for example, this, cow is a female, or this table is 3 feet tall, and so on. These are conditions that hold. They're either true or false. But you might want to actually talk about individuals. That is, you may want to talk about Joe and Jim and Mary and Sarah and so on. So you might want to actually talk about individuals, and you might want to basically talk about relationships between individuals. And one basic relationship is actually that of equality. So you introduce yourself these constants, and even though we're calling them constants, they really are, in a logical sense, variables. The only relation kind of you give yourself is that of equality. So you can say of two constants that they are equal, or you can say the negation of these, that you can say they're not equal to each other. And so now you're going to interpret these constants with respect to a domain. And so you give yourself some set that you might interpret these constants. So for instance, maybe these constants range over the names of people, the participants in this summer school. So you give yourself these names, and you have them range over the domain, which are the actual people that are involved. And you can interpret, like, for example, someone, a person might go by two different names. So you can say that, okay, those two names are actually equal in the sense that they correspond to the same person. So that's what the equality here is. And it's quite important to kind of have this constraint that the interpretation of equality as a symbol in the language is that of identity in the model. And the reason for this is that, supposing it weren't, then given that, equality has to be this kind of equivalence relation, at least in this limited logic, then you may as well build the quotient of your domain and then, merge those things into a single individual so that you can just say it's just identity. Okay, so that's what is going on there. So equality in the language is interpreted as identity in the interpretation. Now, these are the kind of sequent rules for equality, and unfortunately, they're not terribly elegant. I mean, the sequent calculus was just spectacularly beautiful. These equality rules are really awkward, and I think it's a nice open problem if you can come up with a more beautiful set of rules for equality than this. So there's no symmetry to them in the sense of left and right, as you had the others. So these are essentially natural reduction rules. So you can think of this as, you're assuming equality is reflexive as an axiom. You're assuming that, equality is commutative. So if A is equal to B, then B is equal to A as well, because that's what, since it means identity in the model, it means that if A and B have identical interpretations, B and A also have identical interpretations. And you assume that it's transitive. That is, if you can derive A equals B and you can derive B equals C, then from this you can derive A equals C. Okay, so now, just like with propositional logic, this logic too is decidable. And you can actually show that any valid statement in this logic can be mechanically established. Now, you don't just want to talk about individuals. You may want to talk about relationships between individuals. You might say, for example, X studies at this university. You might say, for example, X and Y are brothers, sisters. X and Y belong to the same family. So all of these things can be captured in this. And you might want to actually talk about functions on these. You might say X is the father of Y, for instance. So that's what these language extensions with functions and predicate symbols mean. So functions are going to be these n-ary operators. So they operate on n terms. So now a term is built from a variable or a constant with an n-ary function symbol applied to n smaller terms. So that's what you give yourself here. So you've extended the logic now with term equality. Right? So you've actually added the idea that you can have functions like father, grandfather, ancestor, and so on. That not ancestor, but you can have father, grandfather, mother, sister, and so on as functions. Even sister is not a good choice for a function because you can have multiple sisters, but you expect to have a unique father and a unique mother. Now with these, you have one, the interpretation again is that each n-ary function turns into an n-ary total map on the domain. So it takes n domain elements to a single domain element. It maps. So that's the MF is the interpretation of the function f in the model in the structure M. And the interpretation of equality is unchanged. Equality is identity. The interpretation of a term of this form is again denotational. That is, it's the interpretation of f as a map applied to the interpretations of A1 to AN. Right? So those are the interpretations. So again, in this case, you can only build terms from constants. So and constants are just zero-ary function symbols. One additional rule of inference shows up in this, which is that if you want to derive something of the form f of A1 through AN equals f of B1 through Bn, one way of doing that is by showing that AI is equal to BI for each I. So if you can derive each of those individually, you're allowed to conclude that. Of course, there are other ways of showing f of A is equal to f of B than showing A is equal to B. You could do it by transitivity. You could do it by reflexivity. So these are perfectly fine ways of showing this. Any questions at this point?
Sorry, how is this basically like a fragment of the first order logic in which we are
It
dealing
is,
with terms?
It's a very small fragment. Yeah, that's right.
Okay, thanks.
I'm just trying to kind of introduce, I'm unpeeling the onion. I'm peeling the onion, sorry.
So what actually constitutes a term? A term is a function, basically.
It's a function applied to n smaller terms. It's an n-ary function applied to n smaller terms.
Right, and the term is, I guess, a constant. Like
The base case is a constant. So, essentially a zero-ary function symbol you can see as a constant because you don't need to apply it to any arguments. And so you can, for example, if C is a constant and F is a function, terms you can build are C, F of C, F of F of C, F of F of F of C, and so on.
I see, yeah. Thanks. And congruence, that's something you would want to prove. I mean, I guess it kind of looks self-evident, but it's still something.
That's how axioms and inference rules should be. They should be self-evident.
Yeah. Okay. Thanks.
Because remember, in the other case, I mean, there's no, with just the rules of reflexivity, transitivity, and permutability, and so on. There's no way to actually move equality up a term, but to propagate equality, there's no way of doing that. So the congruence is needed in order to do that. And really, all it means is that if you, essentially, if you apply, f to two equal things, you get two equal results.
Thank you.
So here's an interesting kind of, thing that you might want to prove, that if f of a is equal to f of a, then f of a is equal to f of a. And so you can do this basically by applying the transitivity rule and introducing this idea that you're first going to prove that f to the 5 of a is equal to f to the 3 of a, and then you're going to separately prove that f to the 3 of a equals f to the 3 of a. And this one is just the axiom because it already occurs on the left-hand side. Okay. And out here, you can actually then apply congruence in successive steps to peel off one f, then another f, until you're left with the same axiom here, which is the f to the 3 of a is equal to f of a. And some exercises there for you, right? So now we start introducing a concept of variables. So we extend the language with these variables, and so you have, now just this very simple logic in which all you have, the only formulas you have are s equals t, and so everything is in the form, s equals t is provable. And so you can just add the rules reflexivity, symmetry, and congruence, and instantiation. And so this is just equational logic. So you can basically then say that, from a given set of equations, gamma, I can derive s equals t. Right? So this is the, it's pure equational logic. So once you have equational logic, just dealing with judgments that are pure equations, you get quite a lot. You can start talking about semigroups, monoids, groups, commutative groups, and so on. Within equational logic, by essentially giving yourself the idea is that you have some generators, and you can then talk about a presentation of these in terms of a set of equations that you can use. So you can say, for example, that you have something is associative, something is commutative, and so on. You have a inverse operation, a right inverse operation. All of these things now become available to you. And one thing that I want to emphasize out here, I think I may have mentioned it yesterday, is that you kind of have two different goals in mind when you're formalizing something. Sometimes you want to completely characterize something exactly. It's like you want to characterize what arithmetic on numbers is exactly. And so you would like to enumerate the axioms that in such a way that you characterize exactly the only interpretation that's allowed are the arithmetic numbers. Other times you're only using the axiom as a kind of module for packaging a set of structures. So you want to prove theorems about any interpretation of these set of structures. And in some ways, pure first order logic is that. It's saying that you can just give me any function symbol f, any predicate symbol p. I don't care what the interpretation of these is. You can interpret them as belonging to the same family. You can interpret them as father, mother, etc. This is not something that the formalization is sensitive to, because you want to derive conclusions that hold across all interpretations. So that's also what's going on with, in some sense, the kind of universal algebraic approach, which is that you are basically saying, I'm talking about a family of structures. Any family of structures that satisfies these axioms has these properties. And that's typically what's going on. Now, we know that this idea of characterizing something uniquely, at least for anything that's as expressive as arithmetic, is doomed to fail. Now, we're always going to be missing axioms. We can't, we're always going to admit things that you may not have intended. But that's okay. In some sense, you're still proving theorems about those structures. So what you have lost in completeness, you gained in generality. Okay. Okay, so these are some exercises. Now we move to first order logic. Again, you add a set of variables. The terms now can be built. So the terms can now be built from variables, constants, which are zero-ary function symbols, as well as function operators. Okay, so another new thing here is that you've added these predicate symbols q applied to n smaller terms. So you can say, for instance, that x is greater than y. You can say x is y's brother or mother-in-law and things like that. You can actually have those kinds of concepts as relations out here. And a further extension are these two quantifier operators. So you can say, for all x something holds, or there exists x something holds. Because as we saw with satisfiability and unsatisfiability, when you're solving equations, you're basically trying to say, okay, there is no solution, for instance, and that's a universal statement. Or there is a solution, and that's an existential statement. And sometimes you want to say, well, if you can solve this problem, then I can solve this problem. So that means you're saying that, well, if you can show something exists, I can use that to show something else exists. And that's kind of what mathematics appears to be about. And now the interpretation of these, as I said, does mean that I have to indicate to you what is fixed as interpretation and what changes. So in order to interpret the variables, you need to now add something. So you have this structure M, which gives you an interpretation for the function symbols. It gives you an interpretation for the predicate symbols as well. So you can take a predicate symbol like Q and interpret it as greater than, for instance, in the model. And so the interpretation is basically from the n tuple. If Q is an n-ary predicate, then it's a map from the n tuple to the truth values, true or false. Additionally, you carry around an assignment that interprets the variables. That is, it says that for the variables, for the free variables, actually, I'm going to give an assignment that is in the domain of this thing, of the model. So the model has this domain, absolute value of n, and you're going to pick out values from that to assign to the variables. So for example, if you're interpreting them over the numbers, you might assign variable x to be 0 and y to be 7, for instance.
Sorry, what does d to the n mean?
This is the n tuple of d. So it's D, Cartesian product of D with D with D with D n times.
Okay.
So yeah, it just means that it maps kind of an n tuple of D's in the domain. The domain is really this absolute value of n. Now the interpretation then in the model with respect to the assignment row of Q A1 through AN is that it's doing this thing, the MQ applied to the interpretations at A1 through AN. And remember, MQ applied to these domain elements that are returned by M of A1 through M of AN is going to be a truth value. It's going to be true or false. Similarly, the interpretation of the universal quantifier for all XA with respect to rho is obtained by essentially scanning every domain element little d and seeing if A is holds for each assignment of little d to x. So you're essentially checking that, if you can substitute 0, say the interpretations over the natural numbers, then you're checking, does it hold for 0? Does it hold for 1, 2, 3, 4, 5, 6, all the way. So that's what you're doing out here. And you might think this is really a classic example of a circular definition. There's a for all on the left here, and there's a for all on the right here. And of course, this for all on the right is our intuitive interpretation of for all, and the for all on the left is the symbol in the logic. The main thing, I mean, while there is the circularity, the main thing to understand is that we are fixing the interpretation of for all to be this. So for all isn't a symbol with a
So can I ask a question?
The way Q or F would be. Yeah, Ron, yeah.
So this is a couple of things. So M is a I've seen this before. It's a function that takes the syntax to the mathematical domain, and
yeah, it's a meaning function. Yeah. So it's not, M is not that function actually. It's this whole thing that is the operation. It's the whole thing here. So M is a structure. So M is a structure. So it consists of a domain D and a set of interpretations for the function symbols and the predicate symbols.
All right. So you can use the same letter M for all these different pieces of syntax, basically.
Yeah. So this whole definition is parameterized in M.
Mm-hmm.
So for each, if you gave me a different M, it's the same definition. Just
the second two lines, they seem, I guess, are they equal? The second two lines. So when you have for all X A, and then you also have M of the tuple Q A1 to AN, they seem like the same thing because each M is applied to each of the individual terms inside.
Yeah, so that's a little different. So what's going on there is that your language actually contained A1 through AN. And so you're taking the meaning of each of those A1, A2, A3, A4. Whereas here, you're actually scanning over the domain elements. And the domain elements are whatever you started with. You gave me a structure, and it might have had 10 domain elements. It might have had uncountably many domain elements. But the for all is just going to test whether A is true with respect to each such assignment.
All right. So it works for like. Because I figured the first one could also represent like infinity.
No, these terms are not there. They're bounded.
Okay.
Like 3, 5, or 7, or so on. So it's a fixed. I mean, you're talking about a finite language. So all of this is really, you're when you're doing logic, you're actually bottling lightning. So you're trying to take something that's infinite and possibly uncountably infinite and capture it in a finite language. So and similarly, the existential quantifier is dual. So here, so for all you have for some. For some domain element, the meaning of A with row extended with the assignment D for X is true, then the existential quantifier is true. If there's no such element, then it's false. Okay, now atomic formulas are either going to be equalities or they're going to be things of the form Q, A1 through N. And remember, Q can be a zero predicate symbol, which makes it similar to a propositional variable. Okay, so the main thing here is that nothing much changes. You don't have to, do anything significant for the fact that you made so many extensions to logic. You added predicate symbols and so on. So all of the things that you have. Actually, there's one thing you do need. I forgot. You do need a congruence rule for predicates. You do need to know that if AI equals BI, then Q of AI1 through AN implies Q of B1 through BN. So that's missing. So you do need that rule. So let me write that down. You do need to know that if G you don't need the parentheses, then let's do this. So you do need that. Okay, then you have again this symmetry restored with respect to the quantifier rules. So let's look at the right for all rule. So let me get rid of this. So let's look at the right for all rule. If I asked you to prove some theorem of the form for all x something, how would you go about proving it?
I assume like you take for some specific values and try to prove for those first.
But that's something you could do. If I say, prove for all x something, you could say, let me try it for 0, let me try it for 1, and so on. But here you don't have access to the kind of interpretation. You don't know the zeros and ones and so on. So, if I told you prove that, Goldbach's conjecture or something like that, so you would essentially try you try to prove it for an arbitrary instance of it, right? You'd say, if I'm trying to prove for all x, p of x, let me take an arbitrary x and prove something off of it. And that's actually what is going on out here. So this constant c out here represents an arbitrary choice of x. And because you choose c to be new, it means that, you don't, gamma didn't say anything about c, delta didn't say anything about c. So your C is genuinely arbitrary. That's you're free to interpret C as any domain element. And because of that, when you prove what is above the line there, you've actually proved for all XA. So that's, again, it corresponds to these rules in PVS of columns, column bang, skip star, and so on. So those are the rules that correspond to this column step. On the other hand, if I said, using for all XA, try to prove delta, How would you use for all XA? So, say I gave you the pigeonhole principle and said, you can, the pigeonhole principle is of the form, for all n, there's no injection from n plus 1 to n, say. How
I
would you
guess
use the pigeonhole principle?
show that an arbitrary selection will hold. That way, if it wouldn't matter what you pick and it still holds, then you can draw the conclusion.
No, that's if you're proving the pigeonhole principle. But if you're using the pigeonhole principle, how would you do it?
Choose a concrete instant of X and then use that to prove it.
That's right, yeah. So you would essentially say, oh, that's great. I can use a plus b for n, for instance. Okay, and use that in proving it. So that's what this is. Essentially, you can take any term and substitute it for the x and use the corresponding instance for all xa in your proof. Because you gave me for all xa, so I can use any instance of it. So I can substitute the term a plus b for it and use that instance. So you saw me do that in the proof of everybody loves my baby, for instance. I was bringing in these lemmas. They had universal quantifiers. I was instantiating them and making use of the instance in my proof.
So is T? Go ahead, please.
Are you selecting? Are you selecting for T there?
Oh yeah,
So,
T is any term you want. I mean, you can plug in any term and substitute that.
Isn't it like you're hoping to get lucky? I don't know if I'm saying this right. You're saying,
there is some. In fact, this is a significant point, which is that the choice of T is actually something that involves some insight because it involves some creativity. Yeah.
Okay.
So that.
So does T appear in gamma at all? Do we know anything about T, or it's arbitrary?
T can appear in gamma. There's no. I mean, in fact, often it would, because you're trying to instantiate it with something that actually is there already. So when you saw me instantiate the X in the everybody loves my baby with my baby itself, okay, my baby already appeared in there, so I was using that.
Okay.
Okay, so these rules are dual. Actually, you can see that these two are similar and those two are similar. So in particular, what you see here is that if I told you, there exists XA is something you can use in your proof, okay, then what you'll say is that, that form of there exists XA is awkward because it's the existential quantifier is blocking the A. So I want to be able to make use of it in a way. I want to open up the A for the rest of the proof. So what I do is I pick an arbitrary C and say, whatever it was that existed, that you claim existed, let me call it C. And then I can say, let's replace X with C and make use of that version of A. So that now in whatever else I'm building, I can use C as a building block. So it's exactly like this, in that C must be fresh, because I gave you, the only information I gave you is that exists XA. I didn't say anything about that. The X that exists is actually equal to something else that you have in gamma or delta. If you could make use of that, then that would be unfair, because that might not be the X that existed. So you have to pick an arbitrary C out here, and that's the idea. That because it's completely arbitrarily chosen, then if you told me, well, the X that existed is actually 17, then I can say it doesn't matter. 17 is great. C can be interpreted as 17. On the other side, if you're trying to prove an existential formula, how would you prove it?
Prove it for a specific individual and then say you've got the existence.
Yeah, so you would actually demonstrate it by constructing such an X, right? And so you would actually create a term of that form. You would actually create a construction of this. So for instance, the Ramsey theorem essentially says that for any number of reds and number of blues, there exists a graph that contains either a kind of homogeneous k-clique of reds or I mean, actually, you can think of it, say, it either creates a k-clique of reds or a j-clique of blues. Okay? So you can think of, that's what the Ramsey theorem wants you to do. And the way you do it is by actually saying that, here's a kind of number that I can give you, like for the case of 3 and 3, I can give you that 6 is a number, such that any graph of size 6 contains either a 3 blue clique or a 3 red clique. Right? You construct that graph. So that's what this is. So you're proving that such a thing does exist by actually constructing it. And in constructing it, you can make use of the raw material that you have available to you from gamma and delta. And often you would do that. Okay, so those are the rules.
I'm a bit confused on the proving the for all, because if you have like a proposition where, like you say, x equals 1, 3, or 5, and then you would have to show for all those cases to prove that. You cannot just choose one value. If I'm thinking about it.
Yeah, I mean, so often that does happen. I mean, sometimes you're told prove something, given that there exists an x such that a of x or b of x. So you have to combine the rules in order to do it. So you'll basically have to show that okay, let's call the thing that exists C. Let's do a case in which it's A of C that holds, and let's do another case where B of C holds. And so you can actually try and prove things that way. So this actually, Stephane will talk about later, this particular thing. It's called I think the drinker's paradox or something like that. So it's a problem that Stephane will talk about later on. So I'll skip it for now. Let's just see how it's going. So you can, I mean, once you have first order logic, there's a lot of kind of mathematics you can formalize with first order logic, and you can prove many of these theorems. So these are all exercises you can do. You can talk about actually first order formulas that specify the cardinalities of models that are acceptable and so on. But there are limits. So there are things where you can say of a relation that it's transitively closed, but you can't actually talk about one relation actually being the transitive closure. The things that like transitive closure, finiteness, and so on are actually inexpressible in first order logic. These exercises are meant to give you some intuition as to what you can or cannot do with first order logic. So then let's get into SMT solving as an extension of what we saw as the CDCL procedure. Now that you have first order logic, you can start adding axioms. For instance, you can start adding axioms about arithmetic. You can add definitions of plus, times, less than, and all of these things. You can have arrays, bit vectors as various operations. And you can also have uninterpreted function symbols like this example out here. So you can have, for example, that this is essentially saying, if x equals y, then f of x equals f of y. So that's the example out there. And you can combine. You may have some arithmetic like x minus 2 combined with uninterpreted function symbols. And so you can look at whether this particular formula is satisfiable or unsatisfiable. And you can also combine bit vectors. Now x ranges over bit vectors, and you can combine that with array operations like select and store. So let's look at the case where you similarly you have a bunch of theories, but we'll typically look at one theory. So you might, for example, just have constraints that are given to you with only equality and uninterpreted function symbols, nothing else. Okay. You may have constraints given to you with just equality with this plus operation where you can only add a constant like 0, 1, 2, or 3. So you can only have offsets. You may have constraints that involve difference constraints. So you may have x minus y is less than or equal, is bounded. The difference between x and y is bounded by k. Or you may have linear arithmetic constraints of the form ax1 plus a1 x1 plus a2 x2 plus a3 x3 is less than b. So again, we're going to look at an inference structure. We're going to look at a notion of logical states that have an interpretation lambda as a formula. So as a formula in the signature. The signature is basically the function symbols and the predicate symbols along with their arities. And we're going to have a reduction. Now the turnstile is used for reduction. So you can say that psi1 reduces to psi2. So your psi reduces to psi prime. This reduction step has to be conservative. That is, if psi1 reduces to psi prime, then the interpretation of psi and psi prime as formulas have to be equisatisfiable. The reduction relation has to be well-founded. You can't have infinite sequences of these. And it has to be canonizing. That is, when you reach a certain state that you can no longer reduce, that is, there's no psi prime such that psi can be reduced to psi prime. Okay, that's an irreducible state. Then it's either bottom or it's in a canonical form that actually is satisfiable. And you should be able to read off a model for it. So we'll focus on that. So, resolution is an inference thing and so on. So we can look at that. So we'll skip all this and look at the union find. So in union find, it's a really simple theory where all you have are equalities between variables. That's it. Okay, so your formulas, you're given a set of equalities between variables, and you're told, is this satisfiable or unsatisfiable? You can be given disequalities as well. So I can give you, for instance, x is equal to y is equal to z, and x is not equal to z. Is that satisfiable or unsatisfiable? So this constraint.
Unsatisfiable.
Okay, so this is unsatisfiable. So given the interpretation of equality that we have. And the way you do this is actually by creating these equivalence classes. So every time you hit an equality between x and y, you merge the equivalence classes. As you merge the equivalence class of x with the equivalence class of y. And then when you hit a disequality, you check whether these the two variables that you have, like for example, x and z, are in distinct equivalence classes. If not, you say that it's unsatisfiable. If they are indistinct, you say it's fine. Okay, so that's what this system does. And the way it does this is by actually maintaining a canonical representative for each equivalent class, which is what you get by applying find to it. So here, you have essentially, the input is a bunch of this. So the input is going to be given to you as a collection of equalities or disequalities. So G together with x equals y is the input. And then you maintain this find structure. So when you're given an input, you first check, is this something I already know? So in my, is the find of x the same as find of y? In that case, I say fine. It's not something that I need to add. It's redundant information, and I don't need to do anything. I can just say GN. So that's the easy case. I just deleted x equals y. On the other hand, if the find of x is different from the find of y, then what I do is I say, okay, this I didn't know. This is new information. You're telling me x is equal to y. So let me actually make use of an ordering between the find of x and the find of y, and orient this equation so that your perhaps the lesser is pointing to the greater. Okay? So you orient this equation and you obtain essentially f prime. So get this kind of new oriented equation, and you compose these two. And then this composition of these find operations is going to give you a new set of equivalence classes, where you merge the equivalence class of X with the equivalence class of Y. So this means, what this composition means is that everything that was previously, pointing to the greatest element of the equivalence class of X, is going to be pointing to the greatest element in the equivalence class of Y, if the greatest element in the equivalence class of Y was greater than the greatest element in the equivalence class of X.
So
that's what that means.
It says it's a triple. Is it? It's a pair, or is there something missing? The logical state
is what a pair?
He says the logical state is a triple G F. It should be a pair, or is there?
Oh, sorry. Yeah, that should be a pair. Yeah, that's right. That should be a pair.
I thought maybe it is.
Yeah,
just
I think the reason it's a triple is that I had a different version of it where I was actually saving the disequalities. So imagine I had another component D where I actually saved the disequalities. But instead, what I'm doing here is I'm just kind of being lazy about the disequalities, so that I keep building merging these equivalence classes and treat the disequalities last. So the only rule I need to have about a disequality X equals Y, X not equals Y, is that if f of X is equal to f of Y, then I said that, okay, this is manifestly unsatisfiable. Okay.
Excuse me. So imagine that we want to find all X that satisfy a specific set of constraints. So we should submit the constraints several times to get all the possible X that satisfies the constraint for SM to solve them.
Yeah, so sometimes this isn't doable because you may have infinitely many solutions. But if you do know that this only has like finitely many solutions, then what you can do is you can just say, okay, you told me that X is equal to 3. Now find me a solution where X is not equal to 3. So you can essentially add these kind of blocking constraints that rule out previous solutions. So you can use that to actually enumerate all solutions if you want to.
Okay, so let me explain a scenario. For example, imagine that X should be in a specific interval, I1 and I2. So I want to find the biggest interval that satisfies a set of constraints. I should submit the constraints several times again, or there is other approach to find the biggest interval?
So it depends, actually. In some cases, like for example, in linear arithmetic, you can actually pose this as an optimization problem, and you can actually get the biggest solution the first time around.
Thank you.
Okay. So in SMT, you're augmenting the CDCL procedure with a theory solver like the one we had for union find. And so in addition to the CDCL state that you had with this, H, M, K, C, and the conflict clause gamma, and so on, you also have a theory state S. So the theory state S essentially is just like, for example, the find structure in the union find. And so that's kind of, how you augment the state. And what happens is that these two states, the CDCL state with the propositional, the Boolean information, and the theory state S, actually now start playing a ping pong game with each other. They start kind of, okay, oh, if you know this, then I know this. Well, if it's like you saw with Cheryl and Albert and others. So hey, if you know this, then I can tell you this, and so on. So they start playing this game with each other, and that's exactly kind of what you see in the CDCL, and we'll see this in the case of an example here. So here I mean, this is one where I do have the disequality state, as I told you, That's why that was a triple out there. So here you have a formula of the form y equals z. I mean, these are all clauses. So y equals z is just a unit clause. You have x equals y or x equals z, x not equals y or x not equals z. Okay, so these are your three clauses, and you're going to play this ping pong game. So the first step is you're going to do this CDCL step of asserting y equals z. Okay, so that's what you're asserting, and then the CDCL tells the theory thing, hey, someone just told me y equals z, and so the theory thing says, okay, then in that case I'll make put y and z in the same equivalence class and make z the leader. Okay, so the kind of next step that you do is that you say, okay, I'm going to select that x is so remember this was at level 0, so now I'm going to assert that x is not equal to y. So I just happen to pick this. I just happen to pick this as a thing that I wanted to assert. So I assert that x is not equal to y. The theory thing says, okay, I'll just put that in the disequality state. I'll just say x is not equal to y and hold off on it. But then what you see is that there's a kind of a propagation that can happen. That is, if you know x is not equal to y, then you can actually derive that x is not equal to z. I'm sorry. So you can derive x is not equal to z from this. Okay. So you can essentially get that if y is equal to z and x is not equal to z, then sorry, if y is equal to z and x is not equal to y, then x is also not equal to z, right? I mean, the theory can infer this. The theory basically infers this and says, here's an explanation that goes with it for why x is not equal to z, right? And this is just an application of the congruence rule that the theory is applying. Okay, now, with this, you get a conflict. So you end up with a situation where you have x is not equal to z, and here you have that x is not equal to y and x is not equal to z. So you have a conflict, and then you analyze it, and I can't see the. Give me a second. Okay, so you analyze the conflict, and you get that this lemma holds, that either y is not equal to z or x is equal to y. So that's what you get from the analysis of this conflict in the Davis-Putnam procedure, because you were able to resolve this against that, and similarly do the resolution steps going backwards until you got that is you resolved this clause against that, and continued the resolution until you got this particular clause out of it. Okay, so now in this kind of y not equal to z, x equals y, you can back jump all the way to level 0 and conclude that you have y equals z already at level 0, and because you have y not equals z in the lemma, you can conclude x equals y at level 0, right? So you can get the unit propagation of x equals y out of the conflict clause at level 0. And then, from these two, you can propagate and get x equals z. And, this propagation is just transitivity. And from these two, you get a contradiction because you have, the conflict with this. And because this is a conflict at level 0, you have an unsatisfiable input. So is it clear how this kind of ping pong takes place between the theory solver, that is getting this kind of Boolean information from the CDCL fragment, and then it's deriving possibly theory conflicts from that, as well as theory propagations, and then those theory propagations turn into things that are then sent back to the Boolean solver, and it's able to kind of propagate new information like it did out here.
Excuse me.
So that's basically how an SMT solver works. The
So,
only kind of parameter you can change in this is the theory that's involved. And you can actually deal with a combination of theories, such as you saw with the uninterpreted function symbols and arithmetic and arrays and bit vectors. Okay, question?
yeah. So I want to know that CDCL is the best technique exists. I mean that all the SMT solvers use CDCL technique for driving, obtaining the correct answer.
Yeah, so they do. So this is in many cases actually this conflict-driven approach really works well. So the idea in conflict, a conflict-driven approach is that you wait for a kind of real conflict to arise before you actually do any inference. So we're not exactly doing that here, and that this propagation step here is somewhat proactive, but you could have been lazy about it and held off on it and done it in a more in a lazy manner where you wait for a conflict to arise and then do inference. And CDCL is essentially the standard way of doing the Boolean reasoning in an SMT solver.
Thank you.
Okay, so I'll skip all this and go to higher order logic. Okay, so now in first order logic, you saw that there's basically the way we presented it. There's exactly one universe. So we talked about the domain of the structure. There's one universe and so on. Now you could actually refine first order logic to be many sorted. That is, you could say, okay, there isn't one universe. I'm separating the universe into sorts S1, S2, S3, for instance, and variables range over these sorts. So I might make the distinction, for example, as we did with SMT, as to the sort of numbers, the sort of bit vectors, the sort of arrays. So I could have separate sorts for these. And then I have these select operations, update operations, and bit vector operations as well that are specialized to those sorts. So that's you can have that now. And now what you do in higher order logic is that you start building up more kind of compound structures over these sorts. So you can start as a first step to talk about the tuple type. That is, you could say, I'm going to allow myself the n tuple of things. So that basically allows you to take, n objects and turn them into a single tuple object. So that's what this is. So once you have this kind of, once you have the n tuple, it means that when you have n-ary application, you can turn it into a kind of single application, a single argument. And so all you need are function types that are from one type to the other, because that T1 here could have been a tuple type. So
excuse me.
you have yourself, this T1 arrow T2, which is the kind of function type. And you can think of it as, for example, you can have sorts like bool, nat, real, and T1 could be real and T2 could be real, and you get real arrow real. But you also can imagine that T2 is Boolean, and you get real arrow Boolean or nat arrow Boolean or Boolean arrow Boolean as well. You could have that as an option as well. Yeah, John, who's speaking?
Isn't this kind of redundant to have the type annotation for the bound variable in the lambda abstraction? Because if the lambda term is well typed, then we have the function type for the overall term, from which we can kind of infer that x must have type T1. So if this whole term has type T1 to T2, we already know what x has to be.
So, it is the case that you can do type inference on some of these to some extent, and actually PVS does do that. You don't have to specify the type all the time. But in this case, you're being very explicit about what X range is over, just so that you're not misapplying it. And in many ways, you really do want to provide this information, because what can go wrong is that if you don't provide this information and you infer the type, you might actually find that it's inferred a type you did not intend. So in the case of division, for example, we want to be able to say that the denominator is non-zero. So to be able to specify that you want to introduce division with this kind of type constraint, that the denominator must be non-zero.
Okay, so does it somehow depend on the type theory we are using? Like, for instance, if we have dependent type theory versus, let's say, the Hindley-Milner type system, because I think that at least in Hindley-Milner type system, we should be always able to infer the types of function arguments if we know the type of the function itself.
Correct. Yeah. So you can actually derive the types from the primitive types that you've assigned, and in fact, the way that it's done is actually goes back to this Alan Robinson's unification algorithm to do that. But yeah, here because you're I mean, the reason that's really unhealthy to do is that in some ways you celebrate the redundancy, because the more redundancy you have, the more errors you find. It's possible that you wrote something badly, the type inference algorithm is still able to infer the type, and while that's a convenience, it allowed an error to slip through unnoticed. So you want to be very explicit about these types. So there's a kind of tension between what is called church typing and curry typing. So Curry is the one who actually first introduced this concept of allowing the types to be inferred, leaving them open. And Church insisted that you actually do write down the types explicitly. And my bias is towards this Church view of things, because I value the redundancy. I value the kind of error diagnosis you get from having said this is the type I intend, and if that doesn't work, I need to know.
Okay, thanks.
Yeah. So the semantics is pretty straightforward. A tuple is a Cartesian product. A function is a function space. Now, you can have other semantics for it. This is just the standard semantics for higher order logic. But and there can be other semantics in which it's a more restricted function space, like perhaps the continuous functions and so on. You don't need to exactly be stuck with this. It's the same distinction between many interpretations versus the one true interpretation. So again, you can have, because you have these lambda terms to build these objects in the function type, you can have a rule that actually applies the lambda term through beta reduction. You can say that two functions are equivalent if they are always equal on equal arguments. So that's the extensionality rule. And again, you have similar rules for the tuple operations. You can, just like beta reduction, you can apply projection. And just like extensionality on functions, you get extensionality on tuples. So that if AI is equal to BI for each I, then the tuple consisting of the AIs is equal to the tuple consisting of the BIs. So there are various exercises you can do. I mean, higher order logic is really expressive. Actually, already second order logic is extremely expressive. Most mathematicians don't need to go beyond second order logic to do their work. And a number of logicians actually just study, what expressive power in second order logic is good enough. What lambda abstraction do you need to actually do mathematics just purely in second order logic. But if you're building the machinery, then you may as well go. Why stop at any nth order logic for any n? And so once you have this, you can, for example, represent the sequences of elements of any type as n arrow t, for instance. And once you have sequences, you can get the real numbers. You can start talking about limits. You can start talking about operations like taking the derivative or the integral of a function, because they're all defined by limits. And so it just opens up the whole canvas to doing mathematics. Okay, so I will kind of skip past all these things here. And I won't be able to get to the advanced topics, but I do want to kind of get back to doing a few exercises briefly in the thing. So I want to show you a few things before I let you go. So, here's a kind of example of the same kind of baby.pbs. So previously I had written this axiom in this contrapositive form. So I had actually written this as, loves my baby, X implies X is equal to me. And now if I kind of write it in the contrapositive form, one of the advantages I get is that I can actually use this as a rewrite rule. So in doing this proof, what I can do is I can say, okay, I'm trying to prove my baby equals me. I have to bring in this lemma, everybody loves my baby somehow, because that isn't something I can trigger off of any of this. So what I will say is use everybody. Oops. Yeah. I think okay, maybe. Oh, no, sorry, I mistyped.
There was a typo here.
Yeah. Okay, so I don't think I needed the parentheses, but so that brings in the lemma. That, I mean, the use actually automatically instantiated it and brought it in. It just happened to work. It doesn't always work the way you want it to. And then what I can do is I can just rewrite with the my baby nobody but me. So the advantage of having stated the rule in the contrapositive form is it becomes a rewrite. So that's something that you can then use more effectively. So there is this kind of creativity and taste in actually writing the proofs in such a way that it's convenient to use. Writing the theorems in such a way that they actually become little engines that you can use in building larger proofs, right? So then, if you go back to this, Tarski master theorem, for instance. So again, if you want an intuition as to what exactly happened here, so what is going on is that the thing you're given is a complete semilattice, and you're told that you're told that the operation that you have is you have some monotone operator. So one thing you can get from the fact that it's a monotone operator is that if you take an X, so if you take things in this set, if you take the things in the prefix point, then what happens is that if there's anything in that prefix point, so let's say A is in this prefix point, A is such that f of A is less than A. Okay, then you can keep going. You can go, well, then f of A is less than f of A, right? And hence less than A by transitivity. So you can keep going, downwards. You can keep going, from starting from A, f of A, f of A. You kind of keep going downwards. And because you have a kind of a greatest fixed point, for that you do need the fact that you can't do that anymore. You have to actually start cycling around. One of those f of A's has to basically come back to itself. So that's why the operator f has a fixed point, and the fixed point is really the greatest lower bound of the prefix point. Okay, so that's the explanation as to what is happening out there. And notice this is really everything here is using higher order logic. It's really even though these are first order axioms, x and y's and so on are first order axioms, I'm using a notion of set out here. X is a set. A set is just something from that type T to a Boolean. I'm using the fact that it's monotone as a higher order operation. I'm using it as a second order thing. It's a a predicate on a function. Okay, it's saying that it's monotone. I'm using LFP as a second order operation. It's a least fixed point of a function, and so on. I'm using this fixed point of f, that x is a fixed point of f, as a higher order operator. It takes a function and a first or a single object and says that f of x is equal to x on it, and this is for arbitrary f. So this is kind of a neat illustration of why higher order logic is so effective in formalizing both mathematical concepts as well as computer science. Okay, so I think that is the end of my lectures and the end of this session. There's kind of a lot more in the slides that I didn't get to. I didn't get to Hoare logic. I didn't get to model checking. But we go at the pace that we can manage. So this is stop sharing here, and I can take any questions at this point.
I had some diagram I wanted to share and just to have some discussion about some ideas.
Yeah, let's do that at the end of the day, as I said. Let's defer that to the end of the day.
Okay.
Any other questions?
Excuse me. So about that theory you showed us, Tarski theory, you mean that if we have semi-complete lattice and the function is monotone, you can find a fixed point with limited number of iterations? I mean that there is a limit for number of iterations, or you don't know when you can, the algorithm terminates?
No, actually, it's not limited. The iterations could actually go into the transfinite. This is the kind of amazing power of abstraction. Is that just those few simple axioms capture all kinds. I mean, you literally have bottle lightning, and this is actually such an amazing theorem that let me go back to sharing. So if you go to this theorem called CSB out here, you'll see that I've done a proof of the Cantor-Schroeder-Bernstein theorem using Tarski.
Okay.
So it's what it says is this: if f is an injective function from a to b and g is an injective function from b to a, then there exists an h such that h is a bijection from between a and b. So just check out that proof. You'll see, what a magnificent thing this is. That Tarski master is. But yeah, you can have, these things can involve transfinite iteration.
So we know that with this approach we can find the answer, but we don't know when it stops and give you answer.
And that's how you want it to be. That's the power of abstraction.
Thank you.
Yeah, check out these proofs. I mean, these are all, very, very beautiful proofs, and you will enjoy them. There is a gap in the Hoare logic one. There's a kind of, one proof that's missing. I think I must have made a copying error in copying it over. It's missing out there. But this is nice because that proof is actually quite a hard proof, and you can do that as an exercise. So if you look at this, the second last proof is actually missing out here, the WLP proof. So you can actually see how to finish that proof. But what you see here is the kind of soundness of our logic, that if there is a proof, then it always has a valid conclusion, and the completeness of our logic, that if there's a valid Hoare triple, then it has a proof. And this is in some ways actually a kind of Hoare logic is only relatively complete. It's relatively complete relative to the background logic. So yeah. Any other questions?
Is there a way to download this without using the vagrant to get these files. Number 20.
I will make these files available. They'll be in a folder that I will send the link to.
Okay. And another question is, from the earlier section today, you were saying that there are certain deduction rules that are derivable and some that are only admissible. So that when you are doing derivable, where are you deriving them from? What other rules? Are you deriving them from other rules? Like,
Yeah, actually, I had an example of this earlier in my slides. That is the equivalence rule, for instance. So if you say that if you can prove A is equivalent to B, then in any larger formula F, you can prove that substituting P with A in F is equivalent to substituting B with A in F. So that equivalence rule is derivable. And what it means is that you can essentially construct that subproof corresponding to that inference rule. So an inference rule always takes premises to conclusions. So you can actually construct that the steps in that rule from other rules. So in the case of PVS, these would be what are called proof strategies. Like some of the strategies I showed that I used are actually compound proof strategies, and so they can apply many steps in going from one conclusion to a set of sub goals. So they're similar to derived inference rules.
Okay, so so eventually you have you have some base rules that are all admissible but not derivable.
No. I mean the admissible rules are kind of different beast. So all derived rules are actually admissible, but some rules are like the cut rule is not a derived rule because it is only an admissible rule. So the reason for that is that unlike a derived rule, which you can show that all the inner steps can be filled in with inference rules, for the cut rule to work, you actually need to be given a proof of the premises. So the without the proofs, you can't actually derive the conclusion. So that's the reason it's admissible but not derivable.
So for the
at this point, we're actually making some logical statements that are quite complex. But I hope that you're speaking logic with enough comfort that these convoluted sentences don't challenge you.
So with the derivable ones, you do not need a proof of the premises.
Correct. Yeah, that's right.
Them.
So that's right. All you're saying is that whatever the kind of sequence of steps you need to go from the premises to the conclusion, you can construct those without actually looking at the proof of the premises.
Okay.
And actually, I'm glad you asked these things because this is a very, very important point.
Okay. You can see a derived rule as a macro. You can see it standing for editor subtree made of several rules.
Okay, I see.
I actually have a question. I'm wondering, since the beginning, we saw only sound and complete inference algorithms. So I'm wondering if you could give us an example of unsound and or incomplete inference algorithm, a famous one if possible. So sorry,
I'm muted. Sorry, yeah. So I mentioned the famous example of Frege, who had an unsound proof system. Right, he had an unsound proof system, and that actually caused him great consternation when he got this letter from Russell at Russell's paradox. And so as a result of that, they had to restrict the form of comprehension in set theory, or do something else, like introduce proper classes and proper classes as well to formalize things correctly. Now, in terms of completeness, and this can actually translate into algorithms as well. You can have algorithms with bugs in them, and there was a point at which the SAT competition started getting worried about the fact that many of the SAT solvers were actually unsound, but because they'd been tested on the benchmarks and the competition never really revealed those unsoundnesses. So they started actually demanding that the SAT solvers generate proofs. And if you look at the work of Marijn Heuler, he uses SAT solvers to actually settle large mathematical problems. Some of them involve constructions. Can you show that a construction exists? And that turns into a satisfiable proof assignment. Others turn into, can you show that there is no such thing? And that turns into an unsatisfiable claim. And those claims of unsatisfiability, actually, he can generate proofs for those in a form that's compact enough that you can efficiently evaluate them. And you can even efficiently evaluate them with programs that have been formally proven correct. Now, as far as completeness goes, in many cases, you may or may not care about completeness. You may say, oh, if it proves it, well and good. If it doesn't, it's fine. I can give it some hints and things like that to nudge it along. But there are cases where you would like to know that it is deterministic. That if I give it this problem, it will come back, with either a proof or a counter model, and knowing that is actually really helpful in terms of, say, establishing the completeness of something else that you build on this particular theorem proof that you have. But it's fine to have incomplete things otherwise. It's, as long as pragmatically it gets the job done. And in practice, many things are incomplete, in that they could take forever. They could take a very long time to come back, and you had Control C, you lost completeness.
Thank you.
Okay, we're getting kind of well into the break, so let's stop the recording, and okay, everyone, it's a pleasure to introduce Dr. Stephane Graham-Lengrand. He is a colleague of mine at SRI and has a really amazing track record of accomplishments. He graduated from the University of St. Andrews with a PhD, and then he worked at École Polytechnique before coming to SRI, and he works on a number of projects related to crypto, homomorphic encryption, zero-knowledge proofs, SFD solving, among many other topics. So his lectures on any subject are delightful, and I'm especially pleased to have him talk about type theory. Stephane.
Thank you. Thank you very much. All right, so type theory, what is it? Well, one way of viewing type theory is to see it as an area of logic that's not only concerned with the semantics of formulae, and we've already seen what the semantics of formulae is or can be in terms of truth tables, for instance, Boolean values train calls, but is also concerned with the semantics of proofs. And that's something that we haven't really talked about so far in this workshop. Now, the semantics of proofs may be something that is a bit weird to think about. Maybe something more natural is the semantics of programs. And type theory is actually going to exploit that by basically understanding proofs as programs. This is the proofs as programs paradigm, and Shankar has mentioned it a little bit already. So type theory is based on types, obviously. Types as in a functional programming language. And more precisely, it's based on the type lambda characters. Type theory gives the foundation of a wide range of interactive theorem provers. Here I've got a non-exhaustive list: Koch, Agda, Lean, Matita. And the theorem prover I'm going to use today is going to be Coq. Now I've got a web page here. If you click on it, you actually reach that page here. It's a tutorial on Coq, so that will help you, understanding how the system works. Coq is installed on the VM. In fact, if you go on this web page and download some Coq files, so for instance, hello world here, I can click on it and have it on my VM.
Could you drop the link in the chat?
I can. Let me do that. That should work. And yeah, there it is. Chat. There you go.
Thank you.
You're welcome. So once you have a V file, a V file is a source file for Coq, basically like .pvs is a source file for PVS. You can open it with Emacs, and Emacs is going to be equipped with, is going to call Coq in the background, basically. So that's what you should have here when you open a V file with Emacs. And if you click on next, you actually start processing the V file, processing the script. Okay, so let me know if you don't manage to get there. All right. So here are a couple of sections for today's talk. I'm going to just very briefly review the lambda calculus and simpler types, but Shankar has already talked about it, so this shouldn't be new to you. So in lambda calculus, we have only 3 kinds of constructs: variables, applications, and lambda abstractions. Note that different people have various notations for this symbol behind the lambda x. I think that Shankar uses a colon. Some people use dots, and Coq uses something else. But yeah, just be aware that sometimes the symbol is different. Lambda calculus comes with a very simple typing system. It's the simple typed lambda calculus, and I think Shankar has already shown this rules. So give me a shout if these rules are unfamiliar to you. But basically, yeah, you are deriving the fact that the lambda term, which is here in blue, has some type under some hypotheses about the type of the variables that appear in the term. So delta here stands for a typing context, which is basically assigning some types to the variables, like here. X is assigned type A, and under that condition, you're going to try and prove. You're going to try and type T with type B. All right, the types themselves here, I'm restricting myself to something very small. We only have some base types over which A ranges, and then you can construct a function type from A to B. All right, so lambda x dot x, we've already seen that. This is the identity, and it's the same lambda term as lambda y dot y. These two terms are alpha convertible. Lambda x, lambda y dot x, we've already seen this. This is the first projection, so the function that takes 2 arguments returns the first one, etc., etc. The main notion of computation in lambda calculus is given by beta reduction. When you have a lambda abstraction, lambda x dot t, and this as a whole is applied to some argument, then you can replace x by u in t. And this is one computation step. So little exercise, if you have this slightly more complicated lambda term, what does it reduce to in the end? Lambda x prime dot x prime. And this is applied to an application. On the left of the application, you've got lambda y dot y applied to z. And on the right of the application, you've got lambda y dot y applied to z prime. And I think I've got a parenthesis missing at the end, actually. So anybody can compute in their head what this reduces to?
Z prime?
Yes, it does reduce to z prime. So an interesting thing when you look at this is that you have several ways of actually concluding that. depending on the order in which you reduce, in which you perform these beta reductions. So the left-hand side of a beta reduction here, that kind of situation, that's called the beta redex. And you've got several of them here. You've got one here. That's a beta redex that you can reduce. You've got one here. That's another one that you can reduce. And the whole thing is actually a beta redex because you've got lambda x here. That is applied to a big argument here. So you have three beta reduction steps that you can perform right away. So the question is in which order you're going to do this. If you actually try them all, you realize that they all reduce in the end to z prime. And this is something I'm going to illustrate here in Coq. So on the left here, you've got your script, okay? And we're going to just let the Coq system process each instruction one at a time. So here I'm just introducing z and z prime basically as being two things of a certain type. So Coq is based on a typed version of the lambda calculus. So z and z prime, need to be assigned a type, here A. And then one thing I can do is to actually ask Coq to compute this lambda term here, which is the one that I had on my slide, lambda x prime dot x prime, etc., etc. So you see here that this little symbol here in Coq stands for the dot. So if I ask Coq to compute that, it's going to conclude the same thing as you concluded, and it's written here in the buffer that contains Coq's answers. It's computing z prime, okay, and it doesn't really tell you in which order it has computed it, because it doesn't really matter. Whichever way you decide to reduce the lambda term, it's always going in the end to reduce to z prime. And this is an actual general property of the lambda calculus, which is a consequence of confluence. So what is confluence? Well, it's a concept that you can apply to any relation, binary relation, computation relation, let's say. If t reduces to t1 in an arbitrary number of steps, so this little star here means in an arbitrary number of steps, 0, 1, or more. And if at the same time t also reduces in an arbitrary number of steps to a term t2, then there exists a way of reducing t1 and t2 in a certain number of steps to a common term u. Okay, it's this sort of diamond-shaped diagram. Okay, if t reduces to t1 and to t2, then you can further reduce t1 and t2 to a common term u. So it doesn't really matter whether you go you compute t by going on the left or going on the right. At the end, you're always going to get the same term. Yes, so that's what I was saying here. This is the reflexive and transitive closure of the binary relation. And when I add the little arrow here on the left, it also includes the symmetry. Okay, so we are not, yep. Is there a question?
Yeah, I didn't understand the part you said about the typing context. You mean that in typing context, you assign type for each variable?
Yes.
Okay, thank you.
So you're trying to type a term t, already knowing what the types of t's variables are, and that knowledge is expressed explicitly in this typing context on the left.
So delta is a mapping from variables to types.
Yeah.
Thank you.
Okay, so a corollary of confluence is that if from t you compute what's known as a normal form, an irreducible term, so a term that you can no longer further reduce, then there's only at most one of these terms, okay? Imagine that you reduce t to t1 and t1 happens to be irreducible, then what this confluence diagram says is that, well, t2 has to reduce to t1 and t1 and u are the same, okay? So given a lambda term t, there's at most one irreducible lambda term u to which t reduces. And this is why you don't really care how you reduce things. Coq will not tell you how it reduces it. It just gives you the normal form. Now, this is telling you that there's at most one irreducible lambda term to which a given lambda term reduces to. But does it always exist? Is there always an irreducible lambda term to which a given lambda term reduces? Now, this, what do you think of this lambda term omega? Lambda x dot xx applied basically to itself.
I think by memory, is it some kind of infinite loop?
It is an infinite loop. If you, yeah.
And it's not going to be confluent, I guess, was it?
No, it is going to be confluent. Confluent doesn't really prevent loops. It's just telling you that if you have several ways of reducing, then you have, there exists a way of making those two ways converge, okay, to the same term. But it doesn't say that it's going to converge to an irreducible lambda term, right? And this is what's happening here. In fact, here you only have one way of reducing this. It's the outermost term here. It forms a beta radix, which means that the argument here can take the place of this x here in this sub-expression here. All right, and if you do that, if you do this replacement, where you find that the result is the term omega again. Do you agree?
Yes.
Okay, cool. So this lambda term actually does reduce, and it reduces on itself, and you can do that over and over again, and it's not going to terminate. Now, what if I give this lambda term omega as an argument to lambda x dot y? So what does lambda x dot y do? It takes an argument x, and what does it do with it?
Return y. So y here is free, right?
Y is free, exactly, yeah.
Did it just return y?
I'm sorry?
It returns y.
It returns y, exactly. So it takes its argument x, kind of throws it away, does nothing with it. It just returns y. So the argument here is omega, which has an infinite reduction sequence. It infinitely reduces onto itself. But if you actually reduce the whole term as a beta radix, then you immediately find an irreducible lambda term y. So here it sort of matters a little bit how you reduce things, because if you have a strategy that consists in reducing the argument first, then you are going to diverge to keep on reducing. Whereas if you decide at any point that you're going to reduce the whole term here as a beta radix, then you immediately produce an irreducible lambda term y, having thrown omega away. Yeah, there's a question.
Stephane, I believe John has a question.
Yes.
I don't know if you want
John,
to ask
what's your question?
So since we were discussing type theory just a moment ago, I wonder if there is any logically consistent type theory that allows us to give a type to omega. Because usually I've seen only type theories that require everything to terminate.
Yes.
So,
and this is where I'm going. Can you build a logic, a consistent logic with lambda terms that diverge, basically, that loop? It's a good question, actually. Shankar, do you have?
Actually, the problem here is the self-application. I mean, there's no real way to have a well-founded type system with self-application in it. Right, because if you think of x on the left as a arrow b, then you're going to have to apply that a has got to be itself a arrow b, and so you have a kind of cycle in there. So what you can the best you can do is actually perhaps build type structures in non-well-founded set theory. So there is a whole set theory due to Peter Axel and others called non-well-founded set theory, where you can actually build such sets. So it's possible that in non-well-founded set theories you could find a way of typing these structures.
I
And
had
it's actually, it's a good question because sometimes the non-well-foundedness is useful to you. So I think you'll see examples where you can actually create kind of these streams that are productive, that are actually, doing some work for you. And so it's actually nice to have, for example, terms like omega could be used to represent processes that are kind of self-replicating. So this might actually be a sensible idea.
Okay, thanks.
Okay. But you're right. I mean, this is a perfect segue into my next point, in which in logic we are trying to avoid divergence of these lambda terms that do not return a value because reducing them never terminates. And the reason why some terms are not normalizing, meaning that they do not produce irreducible lambda terms, is that reason is related to issues such as whether applying a function to itself makes mathematical sense. And you can actually look at this question in the more narrow context of the function being a predicate. What does it mean for a predicate to apply to itself? If you think of in terms of set theory, it's also related to whether it makes sense to look at whether a set belongs to itself. Not included in itself, but belongs to itself as a member. So all of this has to do with controlling the domain of the functions that you're talking about. So if you think in terms of set theory, and if you use this notation to say that f is a function from set A to set B, then clearly if you have an inhabitant of set A, then you can apply the function to that inhabitant. It makes sense, and the result belongs to set B. Now, in order to have this kind of control, you actually don't need the whole of set theory. You can have a notion that's a little bit more abstract than set theory. Set theory comes with a lot of axioms, and if the goal is just to control domains and ranges of functions to make sure that it makes sense to apply a function to an argument, you can have something a lot lighter than set theory, and this becomes typing. So the membership relation that you have in set theory, swap that for the being of type A. Okay, and it becomes a syntactic notion, and you can interpret types as sets and recover your the natural understanding of this sentence here in set theory, but you can also leave it more abstract. Okay. All right, so little exercises. Are the following lambda terms typable? Let's take the first one, for instance, lambda x, lambda y, dot yx. Can somebody give me a type for this?
A to B.
So x would have type what?
A.
B.
A to B? Oh, A. Sorry.
A.
Yep. And Y?
A to B.
Yep. And the result would be of
B.
type what?
A to B to B.
Yeah, for the whole
Right.
term. So we can this is a kind of type that we can check in Coq actually. Here, this Coq has this instruction check. It's just going to check that a lambda term here, the one that we've just discussed, can be assigned the type that you've just given. Okay, if we process it, Coq is happy. It's saying yes, it is true that this lambda term has that type. Now, oops. The next one here is also typable. We can check in Coq that the type here is a correct type for this lambda term. So here it means that x is a function from A prime to A, y is a function from the functions from A prime to A prime. All right. So with that, you can apply y to x. It makes sense. It produces something of type A prime. And as something of type A prime, you can pass that as an argument to x and get something of type A. Yeah, does it make sense? Okay.
Is that the most general type you can have for that expression?
Yes, it is the most general type. All right.
So Stephane, you're actually running these and getting some results at the bottom of the right pane, right?
Yeah, this is the buffer for Coq's answers. So whenever you ask Coq to process something on the left in your script, this is my .v file on the left. Coq is going to give its answer here in the little buffer on the bottom right. And in that particular case, when I type check, this is pretty much what I've typed myself on the left. It's just saying I'm okay with this. Yeah. What about this third one? Do you think that we can type this? Now that's going to be difficult because you see that we have both an application of y to x and an application from x to y. So somehow y should be, a function from a to b, x being of type A. And the second application here would require x to be a function, c to d, with y being of type C. But you can't have the two at the same time, because in the first application, y is of type A to B and x of type A, meaning that the type of x is a type that's syntactically smaller than the type of y. Okay, and here in the second application, you have the reverse. The type of y is syntactically smaller as a formula, as an expression than the type of x. Okay, so you can't have the two at the same time. So this lambda term is something that you cannot type, and Coq would refuse any time that you try to give it. All right, so this is just a little activity that's building on what Shankar was presenting earlier this morning.
That's using the fact that the types are syntactically well-founded.
Exactly. Yeah. If you had a particular interpretation of types, then perhaps the type of x being syntactically smaller than the type of y, wouldn't really matter in this particular interpretation of types. And maybe you could find maybe you could find how to type this for a particular instance of typing, but typing at this level remains syntactic, and you don't really know what's A and B and A arrow B sort of stand for. They are up to interpretation, but here the typing activity should, the typing relation should hold whatever the interpretation of the syntax.
Excuse me. So how does Turing compute the type? I mean, it used the type trees or another strategy for finding the type of expressions in language.
I'm sorry, I couldn't hear you very well. Are you asking how do we find the types?
Yes, I mean that the tool you showed us use the type trees for finding the types of expressions.
Yes, it uses the type trees. Types are modeled in Coq as part of the syntax. So here, here you have a type, as a syntactic expression, i.e. a tree. And yeah, Coq is able to understand that tree and understand what the arrow means, etc. So it's got the typing rules that I've shown on the first slide. It's got them built in.
Okay, thank you.
Okay. Now, what about the last? Yep. Is there another remark?
I just had a small question. In the very first example that you gave, could you just like walk me through how you came up with the answer?
Morally speaking, I followed something that we mentioned earlier today, which is Hindemith's W algorithm. Basically, I'm okay. Let's see how we do this. If the whole thing has a type, then what are the rules that I could apply to type the whole thing? So it starts with the lambda, and if we go back to the first slide, there's only one typing rule for lambda. It's this one, right? So if I'm typing a lambda, I already know that the type of the whole thing is a function type, a arrow b. Okay, so I don't know what a and b are, but let's keep them as placeholders. And I know that the last rule I must use to type lambda x dot something something must be this one. Okay, so this is going to happen twice. Okay, I must have used that rule to corresponding to this lambda, and then a second time I must have used that rule in order to type this inner lambda here. Okay, so basically I've got x of some type A, I've got y of some type B, and these are placeholders. Now, what are the constraints on A and B as the types of x and y? Well, I look at the body of the lambda term. It's y applied to x. Now, how could I type this? If I go back to my typing rules, I only have one rule that I can use to type an application. And in this rule, the type of the left-hand side has to be an arrow type, okay? And the type of the application has to be the same as the left-hand side of the arrow type. Okay, so here the A and B are not the ones that I had before, okay? But basically it means that in order to type y applied to x, the type of y has to be an arrow. Okay, so so the placeholder for y's type, which was b, let's call that c arrow d, because I know it's an arrow because it's being applied to x. And then in this application, the type of x, which was a, has to match the left-hand side of this c arrow d. So a has to be equal to c.
Okay, yeah, got it.
Yep. So yeah, that's a particular run of the of a typing algorithm for simple types. Okay, so what are the properties of typing? Well, when you manage to type a term, then all of the free variables of that term must be assigned some types in delta. If delta doesn't assign a type to one particular variable of t, then you're going to have trouble typing C. Okay, so delta covers the free variables of t. The second very interesting property of typing is that it's preserved by reduction, and this is super important. It means that typing is an invariant of computation. If you see that t reduces t prime by beta reduction as your notion of computation, then the fact that the typing of t here as an assumption gives you the typing of t prime means that typing is really an invariant. And the final property, which is super important here, is that this particular typing system for lambda calculus ensures termination, meaning that if t can be assigned type A in some typing context delta, then all reduction paths starting from t are finite. And in particular, this immediately tells you that this lambda term omega, which we've seen before, which reduces to itself and gives you an infinite reduction path, then that clearly cannot be typed in this little typing system. So typing here ensures termination, and the fact that lambda terms produce irreducible lambda terms when you compute them. Okay. So in summary, the lambda calculus, you can see it as modeling the core of functional programming languages, Haskell, ML, etc. And we've already used it in previous lectures as the core of higher order logic in order to construct predicates. Okay, so for instance, here I've got a lambda term. I've sort of indicated the types here as exponents. This is the type of x, little a is the type of x. This is an interesting predicate, actually. It takes two arguments, both of type A, x and y of type A. And what does it say? It constructs a formula that depends on x and y. And the formula is, whichever predicates you have over type A, so prop here is the type of propositions, meaning that A arrow prop is the type of predicates over type A. Okay, so whichever predicate P you have over type A, the fact that X satisfies P, in other words, P applied to X, implies the fact that Y satisfies P, in other words, P applied to Y. So this is saying, give me two things, and I construct the formula that says whatever is true of X is true of Y. Okay, this will play an important role. Okay, so in both cases, when the lambda calculus is used as the core of functional programming languages or in higher order logic, typing plays an important role. And there's a slogan that's attributed to Milner that says, well-typed programs cannot go wrong. This is why we are having typing in the first place. In particular, in higher order logic, typing prevents us from applying a predicate to itself. Okay, P applied to P, you couldn't assign types to this expression. Okay. Now this was super useful because the ability to apply a predicate to itself was allowed in Frege's Foundation for Mathematics, and that led to paradox, which was discovered by Rosser, as Shankar mentioned previously. And here's the letter that Rosser sent to Frege after reading his, I think it was the second volume of the Foundations of Arithmetic, if I remember correctly. There's just one point where I have encountered a difficulty. You state that a function 2 can act as the indeterminate element. This I formerly believed, but now this view seems doubtful to me because of the following contradiction. Let W be the predicate. To be a predicate that cannot be predicated of itself. Can W be predicated of itself? From each answer, its opposite follows. Therefore, we must conclude that W is not a predicate. Now, this is a formulation in natural language that is a bit difficult to parse. And nowadays, the most common way of expressing Rosser's paradox is more in terms of set theory rather than predicates. Now, Frege was kind of depressed by this discovery that his Foundations of Arithmetic was had an inconsistency, stating that a scientist can hardly meet with anything more undesirable than to have the foundation give way just as the work is finished. This position I was put by a letter from Mr. Bertrand Rosser as the work was nearly through the press. So the paradox, Rosser's paradox, it's probably easier nowadays to express it in terms of set theory. And this we can actually do in Coq itself. So this is the next module here. All right, so what do we do? First, we establish a fact, which is a fact of propositional logic, which is that whenever you have a situation in which a formula A is equivalent to its own negation, then you have a contradiction. You have an inconsistency. Okay, this equivalence entails bottom or false. Remember this little symbol here that Shankar has used yesterday? This stands for false. Okay. So this is a little fact of propositional logic, which is not very complicated to prove. Here, I'm just going to use it to illustrate something new that we haven't seen in Coq yet, which is the proof addition mode. It's very similar to PVSs. You have the formula that you want to prove here, and then you're going to use some instructions to manipulate, to complete the proof, basically. So the instructions here would be, hey, okay, let's fix formula A. A is of type prop. Prop is the type of propositions. Now this equivalence, it actually stands for an implication in both directions. So I'm going to split this equivalence into two things. First, that A implies not A, and second, that not A implies A. I'm going to store this in my above the bar. So above the bar here, you have what we call a context of hypotheses. Okay. So you have the fact that A is a proposition, you have the fact that A implies not A, and you have the fact that not A implies A. H1 and H2 here are some sort of indices to help you name your hypotheses. Now, the first thing I'm going to do is to prove not A. So I'm giving myself, I'm going to prove a little lemma, which is not A. Okay, so how do I do that? Well, what is not A? So not A is actually an abbreviation for A implies false. Okay, so what I'm going to do is to try and prove false under the extra hypothesis A. Okay, so what would give me false? Well, H1 would give me false. Okay, H1 here is basically saying A implies false. Okay, this is what's going to give me false. So in code here, I'm just going to say apply H1. Okay. So what will be left is to prove A, which is the premise of H1. And it so happens that I do have A, my context of hypotheses. Okay. So that concludes the literal lemma. I have proved not A. Now let's go back to the main thing I wanted to prove. The main thing I wanted to prove was false under assumptions H1 and H2. And now I've got my literal lemma that I've proved, which is now named H3. Okay. So how do I prove false from these things? Well, I'm going to apply H3 because H3 is not A, which is an abbreviation for A implies false. And I do want to prove false. Okay, so all I've left to do is now to prove A. And how could I prove A? Well, H2 now becomes useful. I haven't used H2 so far. H2 says that not A implies A, and I do want to prove A. So I just say I apply H2, and what will be left is for me to prove not A, which is one of my hypotheses here. Okay, so I just tell Coq to apply H2 here on the left, and Coq is automatically going to understand, okay, this finishes the proof. Okay, so I'm not expecting you to actually, remember all of these instructions to manipulate the proof. In fact, in Coq, since all of this is propositional, here I've got a tactic, a script that would do all of what I've done so far in just one go by doing a little bit of proof search, automated proof search. I tap intuition, and then I just do it, and Coq says, "Okay, I'm done. I've done that for you." Okay. Okay, so this is just a little propositional fact. Why was I proving this fact? Because it's going to be useful for Russell's paradox. Okay, so I'm now going to express Russell's paradox in set theory. So I'm giving myself something that I'm going to call a universe V. Okay, the universe that represents, its inhabitants are sets. Okay, so this is what V is. It's the type of sets, let's say. And I've got a relationship, a binary relationship belongs to between sets. Okay, so it's taking a set, the member, it's taking another set, the thing that the member belongs to, and it's returning a proposition. Okay, and I'm also going to give myself a little notation because it's a bit long to type belongs to. So whenever I write this sharp thing, it means belongs to. So X belongs to Y. This is, you have the ability to define notations in Coq. Now, what was buggy in Frege's system was this comprehension axiom. What does it say? It says, give me a predicate A about sets. Okay, so it's a function that takes a set and returns a proposition. It's a predicate over sets. Now, for any such predicate A, there exists a set C satisfying the following property. Whatever y belongs to C if and only if it satisfies the predicate A. Okay, so for any predicate A, I can construct the set C of all the things that satisfy A. Okay, this is the comprehension axiom. Okay, so if I have this comprehension axiom, I can consider a particular predicate of interest, which is the one that I call not in self. So it's the predicate that takes some input y, a set y, and is stating y does not belong to y. Okay. This is one particular predicate. This is just a definition. So this is how I enter a definition in Coq. I say definition, not in self of y is, and then I give the formula. Now, once I have this comprehension axiom and this particular predicate of a set, I can prove this thing, theorem R, that there exists a set C such that belonging to C is equivalent to satisfying not in self. Okay, it's just one instance of the comprehension axiom when it is applied to this particular predicate not in self. So in Coq, I just claim this as a theorem. So I enter a theorem proving mode here on the right. And I start the proof, and the proof is very simple. It's just, well, apply the comprehension axiom to this particular predicate not in self. Okay, and this is all that happens. Okay. Now this is starting to be dangerous because once I know that there's a set C whose members are exactly all of those members that do not belong to themselves, then I can start proving this next statement, that there exists a set R such that R belongs to R if and only if R does not belong to R. How do we do that? Well, I'm going to apply this theorem R. Okay. Yeah, it's basically the application of theorem R, right? Now, once I have this, it becomes very, very bad. Okay. I can prove false, basically. So you see here, it's a strange term to prove false, but I can prove it in that case because remember this fact about propositional logic. As soon as you have a formula that's equivalent to its own negation, then I have a contradiction. And I am in this situation, unfortunately, okay, because of this R here and the formula R belongs to R. This formula R belongs to R is equivalent to its own negation, and therefore I can apply this propositional fact. Okay, I've got a formula here that's equivalent to its own negation, and applying this propositional fact is going to give me false. Okay, so that was Rosser's paradox expressed in set theory. So you see that you don't need much of set theory to actually reach that contradiction. All we've used was this comprehension axiom. Okay. All right. So the good news is that you can fix set theory, or you can fix Frege's system, which was originally expressed in terms of predicates. And you can fix it in different ways. So Rosser and Whitehead went on to fix this paradox with a theory of types that basically restricts the syntax of statements and basically prevent a predicate from being applied to itself. Okay. If you want to stick to set theory, you can also restrict the comprehension axiom to something called the separation axiom. But if you take Rosser and Whitehead's path of type theory, that path leads to further development by Ramsey and Church, that Shankar already talked about, and basically results in a system which is now called higher order logic. Okay, And there you use the typing system of the lambda calculus to prevent a predicate from being applied to itself. And with this, you avoid Russell's paradox. Okay, so something interesting that I'm not going to talk about is the fact that there's another way of using the typed lambda calculus in logic, not only as a way to write statements, formulas, but also as a way to represent proofs of these formulas. Okay, so this, I think Shankar has already also covered basically. On the left, you've got natural deduction for implication only. This is the axiom rule. This is the elimination of implication. This is the introduction of implication. And if you look at the three rules that we have for typing lambda terms, okay, we've got the rule that's allowing you to type a variable. You just pick the type from the typing context. We've got the rule that allows you to type an application. We've got a rule that allows you to type a lambda abstraction. Okay, and if you look at those two systems, you realize that they're really the same. Yes, the right-hand side here, if you forget about the variables and the lambda terms, then it's exactly the same as the left-hand side. If you read this functional arrow in the type A arrow B as an implication. Okay, so you've got
Excuse
this.
me.
Yeah.
I think the system on the right-hand side has more information, but if we think about just the existence of some term of the type, then it's the same.
So you're right in that there's a little bit more information. For instance, in this axiom rule, imagine that I have several copies of P on the left. Which is the one that I'm using to conclude P on the right? This is left ambiguous in this axiom rule. Whereas on the right-hand side, I could have several things of type A in the typing context. I could have X of type A, but I could also have Y of type A. So the fact that here I'm indicating X of type A is sort of specifying which is the A that I'm using from my context in order to get A, an information which is here on the left, kind of implicit. Yeah. But apart from this, there isn't really much difference. All right, so basically the idea here is that propositions are types and proofs are programs. Basically, they are lambda terms, simply typed lambda terms. So in one direction, you can take a proof tree and you can start annotating it to turn this proof tree into a typing tree for some lambda term. Okay, so the lambda calculus variables are annotating hypotheses, and the lambda term is annotating the conclusion. And conversely, if you have a typing tree for some lambda term t, then by forgetting the variables and the lambda terms or hiding them, basically what you get is a proof tree. This is called the Curry-Howard-de Bruyn isomorphism. What's interesting about this is that when you don't know a proof of a given statement, so you're going to search for a proof. So the activity of proving a given statement, of finding a proof of a given statement, is really the same as the activity of finding an inhabitant of a given type, finding a program that has the correct type. So with this philosophy, proving is really the same as programming. And this philosophy is really what Coq is based on, as well as many other proof assistants. All right, so let's go back to Coq here. Oops. And I'm giving myself a bunch of variables, basically, of type prop. And here if I'm looking for a proof that P implies P, how would that go? Well, typically I would decompose the implication. I would push this P to the left-hand side of the term style, and then I would use an axiom. Okay. If I try to annotate this proof with a lambda term, then I would use the identity lambda term lambda x dot x. Okay. The typing tree for lambda x dot x would be isomorphic to the proof of P implies P. P1 implies P2 implies P1. Same thing, I would decompose those two implications and then use an axiom between the P1, which is now on the left of the turnstile, and the P1 that's on the right. If we try to annotate this proof with a lambda term, the lambda term that we would be using would be a lambda term that we've already seen. It's the lambda term that takes two arguments and returns the first one. Okay, and this is again one that Shankar did. It's a proof of a tautology. This is a tautology whose proof actually corresponds to the lambda term lambda x, lambda y, lambda z, x applied to z, applied to y, applied to z. Okay, so I'm not going to go into the details of this because we've already done it with Shankar. An interesting one is this one. P1 implies P2 implies P1 implies P1. Now, if you use the sequent calculus that Shankar has shown, then you can prove this. However, it becomes difficult to find a lambda term that would be annotating this proof. If I really stick to the proof system that I have here, it actually becomes impossible to prove this formula. Okay, in some sense, those three rules alone are not sufficient to prove this formula here. Okay. However, if you look at this formula and if you construct the truth table for this formula, you realize that this is a valid formula. Whatever the assignment of truth values to P1 and P2, you will find that the truth value that arises to the whole for the whole formula is always true. So this is interesting because it's a formula that's valid, but we don't have a proof of it, at least in this little system with those three rules. And correspondingly, we do not have a lambda term whose type would be this. Okay, and this brings us to intuitionistic logic. We realize that there are some formulae that are valid according to the truth tables constructed on zeros and ones, true and false, but that we cannot prove with this little system, or that we can't see them as types of lambda terms. So let me give you a bit of motivation behind intuitionistic logic. Here's a statement. There's always someone such that if he drinks, everybody drinks. Now, this is natural language. What do you think about this statement? Are you convinced by it? Do you think it's a theorem in general? Or do you have a doubt about it? Any feedback?
It's probably not a theorem.
Okay, interesting. You can formalize this in logic, and this is a formula that Shankar showed on one slide. There exists an X such that drinks of X implies for all Y, drinks of Y. Okay, drinks is just a predicate of RT1 here, okay, in first order logic. Now, it turns out that this is actually provable, at least with the sequent calculus that Shankar showed in its version for first order logic. I'm going to start with an informal proof in natural language. So take the first guy that you see, let's give it a name, like Bob, and you look at whether Bob drinks or not. Okay, if he doesn't drink, then he does satisfy the predicate. If he drinks, everybody drinks. He so happens that he doesn't. Okay, so from false, anything follows. So that's one of two possibilities. The other possibility is that Bob actually drinks. Now, if Bob drinks, then it means that you have to check that everybody else drinks. Okay, so you scan over the other people, and if you find out that everybody else drinks, then you're good. Bob is the person that satisfies the predicate. If he drinks, everybody drinks. Okay. The last possibility that remains is that we find somebody else who doesn't drink. Let's call it Frank. In that case, we're going to change our mind and say, hey, Frank doesn't drink. So let's pick him as the person that satisfies the predicate. If he drinks, everybody drinks. And now we've covered every possibility. Okay. So just by making some case analyses, we have proved informally that there exists somebody such that if it drinks, everybody drinks. Now, you may think that this is just an artifact of natural language. It's not. In fact, you can have a formal proof of this in the sequence calculus for first-order logic that Shankar presented. It's really not very difficult. But what's important about this proof, this formal proof, is that it uses what we call the law of excluded middle. Okay, that from nothing you can deduce P or not P. And we use this in our case analysis when we say either Bob drinks or he doesn't drink. Okay, we are using the law of excluded middle. Now, in Shankar's sequence calculus, you haven't seen this. This we're using it. The problem with this proof is that we have proved the theorem, but at the end, what do we have? We're still incapable of identifying the person that satisfies the property, or rather, the person that satisfies the property depends on the context. It depends on whether other people drink, etc., etc. But we haven't really constructed a term that represents this person that satisfies a property. That we call usually a witness of existence, this term that designates the one object that satisfies a given property. So the logic that we're using doesn't have the witness property. In other words, the logic that we're using lacks a certain dose of constructivism. Let me take another example. Imagine that you have a predicate P.
Stephane, just one point here that it's worth emphasizing this idea that even though the main theorem is that it has an existential quantifier at the outside, but the way you arrived at it is by saying either everybody drinks, or there's some person who doesn't drink, and then that person is the one who exists, such that if he drinks, then others. And so you haven't really provided a witness for the X that is this person. And
exactly.
The other kind of there's a method of proof called the probabilistic method, where you actually show that the probability that something is false is not quite one, and from that you derive existence. That's another kind of way in which things show up non-constructively with this approach of the probabilistic method, that there's a non-zero probability this thing exists, hence it exists.
Yeah. But basically, that's kind of an expectation that we could have as mathematicians, that every time we prove that there exists something, then somehow we must be able to construct that thing that exists and that satisfies the property. And here we haven't done that. Okay. Okay, so here's another example with a predicate P. We don't know much about P. It's a predicate about natural numbers. And all we know is that P of 0 holds and P of 2 doesn't hold. So can we prove that there is an integer X such that P of X and not P of X plus 1? Okay, so this we would be formalizing this question as, hey, can you find a proof of this thing under the hypotheses P of 0 and not P of 2? Can you show there exists an X such that P of X and not P of X plus 1? So it's not very complicated to prove that, again, using the sequence calculus for first order logic that Shankar showed you. What would happen here is that we would basically make a case analysis on P of 1. Does P of 1 hold, or does it not hold? If P of 1 holds, then we can pick X to be 1, okay, because we have P of 1 and we have not P of 1 plus 1, which is P of 2, okay? And if P of 1 doesn't hold, then we could pick X to be 0, because we've got P of 0 and not P of 1, okay? So we can prove that. However, we can't really exhibit a natural number n or an integer n, such that we can prove P of n and not P of n plus 1. Okay?
Is that because
Basically-
P is not decidable?
It's just the proof that we have is doing a case analysis on whether P of 1 holds. It's true that if we could decide, if we could decide whether P of 1 holds, then indeed we could actually produce either 0 or 1, depending on what our decision function gives us on P of 1. But the proof that we have at the moment, in it, you don't find, you can't read the proof and see whether n is 0 or is 1. It's not part of the proof. It's not present in the proof. This witness is not present in the proof.
I see.
And we can actually concretize this by taking P to be this thing. So imagine that you have a sequence, u0 is square root of 2, and ux plus 1 is the previous guy, ux to the power of square root of 2. Now, what do you think of P of 0? So P of 0 is square root of 2 is irrational. That's clearly true, right? What about P of 2? So what's P of 2? What's u2? u2 is u1 to the power of square root of 2, and u1 is u0 to the power of square root of 2. So we've got square root of 2 to the power of square root of 2 times square root of 2. In other words, we've got square root of 2 to the power of 2, and that's 2, right? And 2 happens to be rational. So P of 2 here is clearly false. Okay, so this is a very concrete instantiation of the situation described above, in which we have P of 0 and P of 2. And indeed, we can apply the above, and we can prove that there is an x such that ux is irrational and ux plus 1 is rational. Okay, but that proof depends on whether u1 is rational or irrational. Okay, u1 is square root of 2 to the power of square root of 2. And I have no idea whether it's rational or irrational. Okay, my proof doesn't tell me in which situation I am. All right. So basically, we have a proof that there's a case analysis on whether this is rational. So we've got some kind of mismatch here. When you look at conjunction and universal quantification, there's something nice about these two things. The nice thing about them is that you can prove P and Q if you can prove P and if you can prove Q, and vice versa. Okay, so P and Q is provable if and only if both P is provable and Q is provable. So we've got an object level connective here, the conjunction, and we've got a sort of meta level connective here, and they match each other. Okay, this conjunction matches the meta level conjunction. Same thing with universal quantification. For all x p of x is provable if and only if for all terms t we have p of t is provable. Okay, again, this object level for all matches the meta level for all. This is a remark that Shankar also made this morning. That in fact that there's a match between the object level and the meta level. Now, if we look at disjunction and existential quantification, the situation is not as nice. Clearly, if I've got P is provable, then clearly P or Q is provable. And if I've got Q is provable, again, P or Q is provable. So that direction is good. Similarly, if I can exhibit a term T such that P of T is provable, then I can also show that there exists an x such that P of x is provable. However, the other directions don't work that well, meaning that if you know that there exists an x such that P of x is provable, it's not necessarily the case that you can exhibit an n such that P of n is provable. Okay, we've just seen an example before. typically here, if your property is P of X or not P of X plus 1. You can't really produce the integer n that's going to work. Similarly, if you have P or Q is provable, it's not necessarily clear that you can infer from this that P is provable or that Q is provable. Okay, a very simple example is P or not P. That's clearly provable in one step, but the proof contains nothing. It's not telling you whether P is provable or not P is provable. Okay. And in case, it could be the case that neither is provable. That's called a Gödel formula. Whenever you have a formula P such that neither P is provable nor not P is provable, that's called a Gödel formula. And we know that they exist in logic. So basically the nice match that we had between the object level and the meta level for AND and for OR, we don't have the same match for disjunction and existence. Okay, so we have a mismatch. Yeah.
Is this because the other two, they're quite, I mean, it's a spatial thing. It's almost, the syntax is the same as the semantics. And this final one, I mean, the OR is a inclusive OR, but if it was an exclusive OR, then I guess, I mean, it would be more self-evident. It would not. I feel like it worked.
So here you could have an exclusive OR, right? Because P is incompatible with not P. So in that case, I think that inclusive or exclusive OR would just behave the same. I mean, there would be a mismatch for both, basically. It's just that as mathematicians, we kind of have this expectation that when we prove an existence, then we are able to construct an object that satisfies the property. And whenever we prove a disjunction, we have this expectation that we should be able to prove one of the two sides. And it just so happens that it's not the case with the system that we've seen so far, with the sequence characters that we've seen so far. So in all of our examples, the mismatch is really entirely due to this rule of excluded middle, the fact that we can assume P or not P. There's an equivalent way of formulating the rule of excluded middle, which is the elimination of double negation, the fact that not P implies P. So if you actually want a match, if you're unsatisfied with the fact that from having proved an existence, you can't really construct an object satisfying the property in every time. If you're uneasy with this and want to recover the match, then there's one simple fix, which is to just disallow the law of excluded middle or the elimination of double negation. When you do that, then you get something called intuitionistic logic. And you can do that move, you can make that move for propositional logic, for first order logic, or for higher order logic. Okay. So the claim is that when we make that move, then we'll recover a full match between the subject level and meta level, meaning that first two here, that was already the case. We already had that, okay? But now we are going to have this match on disjunction and existential quantification as well. P or Q is provable if and only if one of them is. And the existent X of the P of X is provable if and only if you can actually exhibit a term such that P of this term is provable. Now,
so Stephane,
note that, yeah?
You can go the other way as well, right? And you can say that, what you're actually saying when you, a constructivist would say that what you're saying when you prove a theorem like the drunkard's paradox is that what you proved is that it doesn't not exist.
Yes. So you sort of mentioned that
you could have done a cock proof of the drunkard's paradox with a double negation in front of it.
Exactly. And you mentioned that yesterday, I think, saying that if you add enough negations in your statement, then you can make a statement that was classically provable but not intuitionistically provable. You can turn that into a statement that's also intuitionistically provable. That's clearly equivalent to the original one. If you have the elimination of double negation. So if you are in one of these situations in which you have a statement that's provable with the law of excluded middle, but it's not provable if you don't have it, then by putting enough negations in it, then you make it intuitionistically provable. So I sort of agree with you, Shankar, that the difference, the two logics kind of agree on what's provable. It's just they disagree on how to write the statements, basically.
So with the law of excluded middle, does it only make sense if the or is an exclusive or?
No.
Because
well, in that case, it so happens that
P
yes,
and you cannot have
P and not P.
Is
that leads to inconsistency in any logic. So here in this particular formula, yes, you can understand this as an exclusive OR, but the question with disjunction is a question that's not specifically about exclusive disjunction.
Because I would have thought if you're using the law of excluded middle, then that means every OR becomes exclusive.
No.
Oh, but how can you have it if it could be an and? Then it doesn't make sense. P and not P.
No, I think the problem was this, that if you have excluded middle, it does allow you to do a case analysis on whether P holds or not P holds, without any kind of sensor or a probe that tells you, which of these things is actually the situation you're dealing with. So that's the real problem, is that neither can you, when you produce a proof that involves that, you can't really give somebody a construction that they can use because they can't sense which situation they're in.
Right. So if you're in one situation, would it convert all of the ORs to exclusive? Or?
No, the exclusive OR is just another connective. This isn't a problem with exclusive OR. Actually, the problem is really about this particular disjunction. What it is when you're doing case analysis in a proof. So when you do a kind of the exclusive OR is a kind of different connective, that where you're claiming that really when you say P exclusive OR Q, one of these situations holds and not the other. So that's kind of what you're saying when you say an exclusive OR.
Excuse me.
And you can capture exclusive OR obviously with conjunction and disjunction.
Okay, thanks.
There was another question?
Yes, I think that in certain technical sense, the disjunction in intuitionistic type theory, it is exclusive in the sense that when we introduce the disjunction, we either inject the left or the right disjunct, and then when we are given the proof object for a disjunction, we have no way knowing that so if you have this P or Q and I give you Q, you have no idea knowing whether or not P was also true.
So yes, I understand what you're saying. Typically here, if you want to prove P or Q, then a typical way of proving this, actually in the empty context, you have no choice but actually to provide a proof of P or to provide a proof of Q. Now you could have a proof of both. So in that case, imagine that you have a proof of P, imagine that you have a proof of Q. Now, if you want to construct a proof of P or Q, you're going to choose which one you use and throw away the other, even though both would work. So in that case, your proof is actually making a choice between, P or Q.
So that's right. I mean, as Stephane showed, type theoretically, the P or Q becomes a disjoint union or a tagged union. And that means really that when you produce a proof of P or Q, you can say, contextually, whether it's a proof of P or a proof of Q. And correspondingly, when you use a proof of P or Q, you can assume that you'll know for each given proof whether it's a proof of P or a proof of Q.
Yeah. So and if it's one of them, it doesn't mean that there is or there isn't a proof of the other. You just don't know, or you don't have it.
Yeah, in fact, I guess if you actually wanted to implement exclusive OR, you'd have to explicitly require that they're also not equal.
Yeah.
They're not also not both true.
Yeah. Now, notice that this nice match, so we call that the disjunction property and the existential property. This nice match works in the empty theory, not in any theory. So if you had something on the left-hand side of the turnstile, then it could break this match. Imagine that on the left-hand side, you have P or Q. Then obviously from P of Q, you can have P or Q, but then you don't know whether you have P or if you have Q, right? And same thing with the existential. If on the left-hand side of your turnstile, you have an axiom or a hypothesis that's telling you the existence of X such that P, then you can obviously derive this existential formula on the right, but you still don't have a term T to exhibit, okay? So this match really only works in the empty theory. Well, at least it works in the empty theory. We're going to see if we can generalize it. All right.
So one thing I want to add is that you'll be seeing lectures later on ACL2, which is a kind of, at its base, a quantifier of free logical recursive functions. And there, actually, you can use the excluded middle because, everything there is actually constructive. So, you can get away with using the exclusive middle because there's a global assumption around the logic.
Okay, so seeking the witness property is a part of a wider approach to mathematics called constructivism, with the central idea being that the objects that mathematics speak about must be constructed. And a typical bad example of non-constructivism is the set of all sets that you can formulate in Frege's original system that Russell showed to be inconsistent. The axiom of comprehension allows you to to speak about the set of all sets, but you haven't really constructed it. And if we can always speak about an object that we have shown to exist, then while showing its existence, we must have constructed it. This is what you want if you're a constructivist. And similarly, if we claim that one of two things holds, we should be able to compute which one of the two holds. And you may have a choice, like we said, but at least we should be able to compute one of those three things that holds. So this notion of constructing things really brought about a very computational view of what it is to do mathematics. Now, you remember that there was one formula, it's actually called Peirce's formula, that if you look at the truth tables, it's clearly valid, but you don't really have an intuitionistic proof of it. So now you have another mismatch between what you can prove and what the truth tables tell you. The truth tables are really originally giving a notion of semantics for your formulae. So the notion of intuitionistic probability no longer matches that semantics. So the question is, can we build the semantics of formulae that would actually match this notion of intuitionistic probability? And this is what we're going to do on this slide. So instead of interpreting a formula A as either 0 or 1, either true or false, we're going to interpret it as a set of things that are called realizers. Okay. So instead of using the usual truth tables, we're going to reason about whether there are realizers of formulae. So whenever there's a realizer R that belongs to the interpretation, to the semantics of formula A, we're usually going to abbreviate this as that, which reads R realizes A. And here are a couple of rules that guide this notion of realizing a formula. We're going to have the rule that R realizes a conjunction if R is a pair of two components called R1 and R2, with R1 realizing P1 and R2 realizing P2. So you construct a realizer of P1 and P2 by putting together in a pair a realizer of P1 and a realizer of P2.
Excuse me.
Yeah.
So it's a form of denotational semantics?
It's a formal denotation of semantics that's there to replace the semantics given by truth tables, so that this new semantics actually matches the intuitionistic notion of probability.
Thank you.
Yeah. And the rule for disjunction is that you realize a disjunction, so R realizes P1 or P2. If R is a pair whose first component is just a bit of information that's telling you whether you are going to realize P1 or realize P2. Okay, so either I equals 1, and in that case, the second component of the pair R prime is a realizer of P1, or the first component of the pair I is 2, and the second component of the pair R prime is a realizer of P2. So the realizer of the disjunction really contains an indication, a bit of information saying which of the two sides you're going to realize. And then the second component of the pair tells you how you realize it. Okay. An alternative way of saying exactly the same thing, which is the one that Koch uses, is talking about injections. Okay, so a realizer of P1 or P2 is of the form inj I of R prime. And if I is 1, then R prime is a realizer of P1. And if I is 2, then R prime is a realizer of P2. Okay, but it's isomorphic. Now, you're going to realize an existential formula that exists in X such that P of X. If you are a pair whose first component is a witness, so an element of your domain, and your second component R prime is a realizer that this witness A does work, in the sense that R prime is a realizer of P of A. So here again, the realizer contains structurally, it contains the witness that works. A. Okay. A bit more interesting are the cases of implication for all. How are you going to realize a formula P1 implies P2? Well, that would be a computable function. So in other words, a program that's able to transform any realizer of P1 into a realizer of P2. Okay, so you realize an implication by exhibiting, by being actually a program that transforms any realizer of P1 into a realizer of P2. And similarly, you're a realizer of for all x P of X. If you're a computable function that's able to take any possible X, any element A of your domain, and from that element, produce a realizer of P of A. Okay. So this is an interesting relationship between realizers and formulas. Notice that this relationship is defined inductively on the structure of the formula. Okay. And it's telling you what should be the corresponding structure of the realizer. What information should the realizer have in order to realize the formula? Now, this is parameterized in the way you interpret atomic formulae. Okay, there are no rules for telling you how to realize an atomic formula. Okay, so these are the rules up there. And the question is, what are really ranges over? I've been a bit implicit about this. Basically, the realizers, if you look at all of the cases here, must allow you to construct pairs of realizers. They must allow you to construct injections of realizers. And they must be able to represent computational functions. Okay. So you can choose realizers to be just natural numbers. Do you see how you can do this? Like it's kind of easy to represent a pair of natural numbers as a natural number. Okay, you have, as we've seen with Shankar, we've got a bijection between between the natural numbers and the pairs of natural numbers. So that's kind of easy. How about computable functions? How can a number be or represent a computable function? Any idea?
Do the numbers need to be natural numbers?
I will allow you to use negative numbers if you want.
Well, my concern was that there are uncountably many computable functions.
That's not the case. There are countably many. There are incountably many functions from n to n, that's true. But if you restrict your attention to the computable ones, then they are countable. Because the computable ones are those that for which you can write a program computing the function. And there are only countably many programs that you can write because programs are made of symbols and sequences of symbols, basically. So there are only countably many programs. And since there are countably many programs, you can number them: program number 0, program number 1, program number 2, etc. So you can use that numbering to index all computable functions, basically. So that's what people did in the 30s, using numbers for realizers. A more modern way of seeing this semantics, this realizability semantics, is to use untyped lambda terms as realizers. Okay, with untyped lambda terms, you can represent pairs, and you can actually represent computable functions, all computable functions actually, because the untyped lambda calculus is Turing complete. And this is where we are brought back to the curry-forward-de Bruijn correspondence. The lambda calculus that you've seen so far just for the connective implication satisfies the following theorem. Basically, if you can type a lambda term m with type p, then you can show that this lambda term is a realizer of p. Okay, and these are two binary relations between programs and types, which are defined differently. The typing relation is defined according to the syntax of the program. Okay, you have a rule for lambda, you have a rule for application, you've got a rule for variable. The realizability relation, the fact that something realizes formula, on the other hand, is defined by induction on the formula itself. Okay, but it is a theorem that if m has type p, then m realizes p. Okay. Now this, so you've seen the lambda calculus with implication or the function type being the only type constructor, but you can actually generalize this to other connectives than implication. In other words, we can extend the lambda calculus to account for introduction and elimination rules of other connectives than implications. Let's do conjunction. You can
Stephane,
interpret. Yeah.
Stephane, can you? We've run out of time, so you can take a few more minutes if you want, but you need to plan an end game.
All right. Just to give you an intuition about what's happening with other connectives, how do you see a conjunction computationally? You can see, or let's say, how do you see a conjunction as a type? You can see the conjunction of P1 and P2 as a product type, P1 times P2, basically. The type of pairs whose first component is in P1, whose second component is in P2. Okay, and you can extend your calculus with tuples, basically, pairs and more generally tuples to account for this. Once you have this, you can prove theorems of that form. P1 and P2 implies P2 and P1, which is just the symmetry of conjunction, and provide a lambda term that actually inhabits this. for disjunction, like Shankar was saying, you can see a disjunction as a sum type. Okay, P1 or P2 is made of things that either live in P1 or live in P2 as a sum type. Okay, and again, you can have syntax for this, which is in the lambda calculus an extension based on pattern matching. And again, you can show with this notion of pattern matching, you can exhibit lambda terms with pattern matching that would be proofs that would represent proofs of symmetry of disjunction. And you can keep on extending the lambda calculus to account for other things, such as quantifiers, for instance. Okay. What I want to finish with is basically the idea that once you understand that in intuitionistic logic, proofs and programs are the same thing, proofs and typed programs are the same thing, then the notion of computation that you have on programs, the fact that beta reduction gives you a way to reduce a lambda term to another lambda term, that's, if you see that in terms of logic, it's telling you that you have a process for transforming proofs. If the lambda term m is now annotating or decorating a proof in logic, then the fact that m reduces to an m prime with m prime satisfying the same typing properties, then what you're doing is really transforming a proof into another proof, okay, which is made of simpler constructs, let's say. Okay, and it's this transformation of proofs that is actually allowing you to have the match between the object level and the meta level. The fact that when you have a lambda term of type there exists an x, then you actually do have the term t, that the witness t. And when you have a lambda term that has P1 or P2 as a type, then you can compute either a proof of P1 or a proof of P2. So there's a really deep connection there between lambda terms inhabiting types and the ability of extracting a witness or extracting a disjunct to satisfy the witness property or the disjunction property. Let me just finish with one little further extension of that idea of Curry-Howard, which is when you actually start talking about natural numbers. Imagine that you want to show this property, which is for any natural number x, there exists a natural number y such that x is equal to y plus y, or x is equal to 1 plus y plus y. So basically y is roughly, well, it is half of x, okay, the floor of half of x, okay? And how are you going to prove this in Coq? A typical way would be to do an induction on x. So can you prove this for x equals 0? Yeah, sure, by taking y to be 0. Now, if you know that this whole thing is true for a particular x, can you show that it also holds for x plus 1? Okay, so you would prove this by induction. Now, when I go through the proof here in Coq, it's actually doing the induction. And you can easily finish the proof. And you've got a proof of this for all exist, okay, a formula. The proof is called half. And what I can do is compute with this proof. If I just check the type of half applied to 25, it's telling me half of 25 has type that exists a y such that 25 is equal to y plus y, or 25 is equal to 1 plus y plus 1. Now, if I decide to compute half of 25 as a lambda term, meaning that there are some beta reductions that apply, then I tell Coq to compute that, and it's going to, I already know that it's going to have the same type, but I already know that the result is going to have the same type as half of 25, namely the fact that there exists a y, which is basically the half of 25. And when I look at the results of having computed half of 25, I see a big thing here. So it looks a bit unreadable, but what is it? It's the introduction rule for the existential quantifier, with here the witness for it, in that case 12, and what comes after is basically a proof that 12 works. Okay, So the proof that I obtained by induction on X is actually a program that's defined by recursion on X. And when I apply this program to 25, I get as an output what I expect, namely 12. So at no point in my script on the left, I ever mentioned 12, but simply by computing the application of this program half to 25, then and reducing it to a normal form, then I do get my answer. So you can compute with proofs. You can have an activity of proving theorems, and the proof of these theorems are actually programs that you can literally run and get answers from. And I'm going to stop here.
Thanks a lot, Stephane. That was amazing. So it's it's nice to see something looking almost like poetry on the right-hand side.
Well, I don't know if the big part here, which is basically the fact that 12 satisfies the spec, is poetry. But I do like seeing this 12 here, come up out of the blue, out of computation, basically.
Very nice. Any questions?
I was wondering, in classical mathematics, is there any other source of non-constructiveness besides, I think, the axiom of choice?
So I think the axiom of choice is actually a little complicated in that I think if you were in a kind of constructive set theory, you could actually have, you could believe in the axiom of choice. But in the case of classical set theory, I mean, the problem is that, there isn't, it just asserts the existence of a choice function without any, way of actually executing the choice. And so that's something that I think makes the use of the axiom of choice more controversial in classical logic.
Mm-hmm. Right.
To complement that answer, if by constructivism we think in terms of programs that compute things, every time that you're actually using an axiom without giving it any computational interpretation, then you're lacking something in terms of, at the point of the program when you just call upon an axiom, you don't have any, if you don't have a computational interpretation of this axiom, then your computation is kind of stuck there because you're calling some kind of oracle that's telling you, hey, I'm able to do that, but having a hole there. So if you want to have constructivism, at least to give it in terms of computation, then you need to give a computational interpretation to all of the axioms that you're using. In that particular case here on the screen, the induction axiom is given computational content by saying, hey, this is recursion. So the axiom of choice, you will need to give a computational interpretation to it. And if you were using any other axiom, you would also need to give a computational interpretation to it.
In some ways, both are really useful in that, I think if you proved a classical result, you're not going to be looking for a constructive version of it. It saves you the trouble of looking for something. And on the other hand, if you really do want a more informative result on which you can compute with, then use the constructive ways of doing proofs, and in particular use logics that might actually constrain you that way.
With the realizers formalization, that is there a set theory formalization of it?
Well, the definition of realizability is entirely done in set theory. I mean, you can also do it in other foundations, but at least the definitions that I've given here, basically you interpret formula A as a set of realizers, and you're giving rules about when it is that a particular realizer is in the interpretation of a particular formula. So you can understand these rules in set theory completely.
Sure. Okay. Thanks.
And in fact, the fact that if you have lambda term m of type P then M is a realizer of P. This is basically looking at the semantics of typing in terms of set theory.
Right. Okay.
Yeah.
Thanks.
Excuse me, I have a question. I'm a little bit confused at how scientists handle recursive functions in lambda calculus and type lambda calculus. How is it possible to compute and define the semantic of recursive functions in type lambda calculus and lambda calculus?
So in the example that I have here, one thing that sort of glossed over is the way that natural numbers are represented. So natural numbers here are a particular kind of what we call inductive types. In PVS, they're called data types, and they have various names, algebraic types, algebraic data types. Now, if you have such types in your typing system, then you would usually have a specific construct for constructing recursive functions by basically giving you some kind of fixed point operator. And you can do all of this in a typed way.
So you mean that we should first find the fixed point, and based on fixed point, we define the recursive functions and their semantics?
Yes. So basically here, the proof that you obtain by induction, if you see it computationally, it's a fixed point defining a function by recursion. Now, in order to make sure that the lambda terms always terminate, there are several restrictions actually, but one of them is that when you define such a recursive function using a fixed point construct, the recursive calls that you make in the body of the definition, the recursive calls have to be on subterms of the original arguments to make sure that something decreases with every recursive call. So in particular here, the function that computes the half, when you pass it an x, it's allowed to call itself recursively on a smaller x, on x minus 1, basically, in that case. So with this restriction in place, then your fixed points and your recursions will terminate.
Okay. Thank you very much.
Sorry, this is actually an excellent question, because if you just take the pure simply type lambda calculus, there's no way to actually do recursion in it, even though you can get some quite complex things defined with it. There's not a way to actually define recursion within it. It's different from lambda calculus, that way where you can get that term omega in there and use omega to actually define a way of presenting recursive functions. The typical way to deal with this is actually to add recursors. So there's a system called Gödel system T, where you actually add primitive recursive operators to allow you to do things like the Ackermann function that is there in the previous examples that I presented. So that's kind of the way that you could augment the simply type lambda calculus to do recursion.
How do you actually specify the subterms when you're doing the recursion? Because usually I just see you call the function itself. But
here, if I
inside,
yeah, if I look at the definition of the natural numbers in Coq, print n, I see here how it's defined. So it's saying it's an inductive type with two constructors. There's a constructor called 0, which allows me to construct a natural number. And there's a second constructor called successor, which takes a natural number and returns a natural number. So if I So from this definition, whenever you have successor of 0, let's say, then, okay, so this is the encoding of 2, but this argument S of 0 is a strict subterm of the whole thing. It's really very syntactic. It's the notion of subterm is completely syntactic, and it comes from the very definition of an inductive type being a subterm of something else. And so it's a syntactic check whenever the function calls itself recursively, that the argument of the recursive call has to be a subterm of the argument of the caller, basically.
So you can use the pattern matching as a way of recording that one thing is a subterm of another.
Yeah, I think I see. Yeah, thank you.
Okay, so that's great. So we've come to the end of the speaking logic lectures. Let's thank Stephane, for this presentation, and we'll, I'll keep the Zoom link open for a bit. But first, I'm going to switch off the recording, and then we can continue the conversation.